something strange happens when you shine light through two slits. You expect two bright lines, one for each slit. But instead, you get many of a ripple pattern, as if light were a wave. Then you slow it down one photon at a time. Still, the pattern appears. Each photon acts like it passes through both slits at once. But the moment you watch, it changes. The pattern vanishes. Reality behaves differently just because it's being observed. Hello there, and welcome to the Sleepy Lab channel. I'm glad you're here tonight. Maybe it's late, and your mind's still awake, searching for something to wonder about. Tonight, we're descending into the quantum world, the foundation of everything. A place where observation shapes reality, and where light itself seems to know when it's being watched. Here, certainty dissolves into possibility, and the universe starts to look more like a dream. You don't have to understand any of it. Just let the ideas drift past, like ripples of light. Before we continue, I'm curious. How far does this little lab reach tonight? Tell me where you're listening from, and what time it is for you right now. I read every comment, and it always amazes me how far this journey travels. And if you find peace in these quiet explorations, consider liking and subscribing, but only if you truly want to wander with us again. Now, take a breath, and let's begin our descent into the quantum world. Everything is made of quantum particles that follow rules completely unlike our everyday world. Right now, beneath your awareness, the atoms in your body are doing something impossible. They're existing in multiple states simultaneously, flickering between possibilities, following rules that would make no sense if you could see them directly. Every solid object around you, every breath you take, every photon of light touching your skin, all of it operates according to quantum mechanics. These aren't the clean, predictable laws of the world you see. At the quantum scale, particles don't have definite positions until you look at them. They don't follow predetermined paths. They exist as clouds of probability, waves of potential, choosing their reality only when forced to by interaction with the larger world. Your coffee cup sitting on the table seems solid and certain, but zoom in far enough, and you'd find a storm of quantum uncertainty, particles winking in and out of definite states trillions of times each second. Yet somehow, from all this quantum strangeness, the reliable, solid world emerges. The keyboard beneath your fingers, the weight of your body, the light in the room, all of it built from particles that individually refuse to follow the rules of common sense. Quantum mechanics emerged when scientists discovered light behaves as both waves and particles. For centuries, physicists argued about what light truly was. Some experiments showed light acting like waves, rippling and interfering with itself, bending around corners. Other experiments showed light acting like particles, tiny packets of energy striking surfaces one at a time. Both sides had evidence. Both sides were right. In the early 1900s, this contradiction became impossible to ignore. Max Planck discovered that light is emitted and absorbed in discrete chunks he called quanta. Einstein showed that light knocks electrons out of metal as if it were made of particles, not waves. Yet the wave nature of light was undeniable, proven in countless experiments. Slowly, reluctantly, physicists realized they needed a new kind of physics. Light wasn't either a wave or a particle. It was both, depending on how you looked at it. This wasn't a limitation of human knowledge or measurement. It was nature revealing something profound about reality itself. Wave-particle duality became the first hint that the quantum world operates by rules we never imagined. From this strange discovery, quantum mechanics was born, and our understanding of reality would never be the same. The word quantum means the smallest possible discrete unit of any physical property. The word quantum comes from the Latin quantus, meaning how much. In physics, It refers to the smallest amount of any physical property that can exist independently. Energy doesn't flow in a smooth, continuous stream at the quantum level. It comes in packets, in steps, in discrete units that cannot be divided further. An electron orbiting an atom can't have just any amount of energy. It must occupy specific energy levels, quantum states with precise values. When it jumps between these levels, it does so instantly, without passing through the space between. There is no in-between. Light, too, comes in these irreducible units called photons. You cannot have half a photon. Electric charge comes in quantum units. The charge of an electron is the smallest unit of charge that exists freely in nature. Angular momentum, the spinning motion of particles, also comes in quantum packets. This discreteness, this graininess of reality at the smallest scales, is what quantum means. It's nature's way of saying that at the foundation of everything, existence itself is not smooth and continuous, but comes in tiny, indivisible pieces. The universe is made of pixels, in a sense, though far smaller and stranger than any screen you've ever seen. Quantum physics describes the universe at its most fundamental level, smaller than atoms. When you look at the world around you, you're seeing the consequences of quantum behavior, not quantum behavior itself. The quantum realm exists at scales far below what your eyes can detect. An atom is already incredibly small, about 10 billion times smaller than a millimeter. But quantum effects govern the particles that make up atoms, electrons, protons, neutrons. Go even smaller, and you find quarks and gluons, the particles that make up protons and neutrons. At these scales, the familiar laws of motion and gravity become secondary. Quantum laws take over completely. Particles don't follow predetermined paths. They exist in superpositions, blurred across multiple states simultaneously. Time and space become fuzzy. Cause and effect blur at the edges. Yet from this strange quantum foundation, everything you've ever known emerges. The solidity of matter, the flow of electricity, the light of the sun, the chemical reactions in your cells, all of it rests on quantum mechanics. You are made of quantum particles. Your thoughts arise from quantum interactions between neurons. But you don't experience the quantum world directly because you're too big, too warm, too entangled with your environment. The quantum world is hidden from everyday experience, but it's always there, underneath everything, the deepest layer of reality. The equations of quantum mechanics are among the most precisely tested in all of science. Quantum mechanics makes predictions that have been tested to extraordinary precision, and it passes every test. The magnetic moment of the electron, for example, has been calculated using quantum electrodynamics and measured experimentally. The two numbers agree to 10 decimal places, making it one of the most precisely verified predictions in all of science. Quantum mechanics predicted the existence of antimatter before it was discovered. It explained the stability of atoms when classical physics said they should collapse. It predicted the laser, the transistor, the behavior of superfluids and superconductors. GPS satellites have to account for quantum effects to give you accurate directions. MRI machines rely on quantum mechanics to image your body. The computer or phone you're using right now functions because engineers understand how electrons behave quantum mechanically in semiconductors. Despite its strangeness, despite the philosophical puzzles it raises, quantum mechanics works. It has never failed a test. It describes nature with breathtaking accuracy. The equations may seem abstract, filled with complex numbers and probability waves, but they map onto reality with astonishing fidelity. Whatever quantum mechanics is trying to tell us about the nature of reality, it's not just philosophy or speculation. It's the most successful scientific theory ever devised. Light travels as a wave but arrives as a particle. When light moves through space, it behaves like a wave, spreading out, diffracting around obstacles, creating interference patterns. But when light interacts with matter, when it's absorbed by an atom or detected by your eye, it arrives as a particle, a discrete packet of energy called a photon. This isn't just a matter of perspective or measurement technique. Light genuinely exhibits both natures. Send a beam of light through a narrow slit, and it spreads out in a diffraction pattern, exactly like water waves passing through an opening. The intensity of the light at any point is determined by the constructive and destructive interference of waves. But place a detector to measure the light, and you'll record individual clicks, one photon at a time. Each photon is indivisible, a quantum of electromagnetic energy. You can't split a photon in half. It's absorbed all at once or not at all. The energy of each photon depends on its wavelength, connecting its wave nature to its particle nature. Blue light photons carry more energy than red light photons because blue light has a shorter wavelength. This wave-particle duality isn't a contradiction to be resolved. It's a fundamental aspect of how light exists. Neither description alone captures the full reality. Light is something richer and stranger than either waves or particles, something our everyday language struggles to express. Electrons can pass through two openings simultaneously when not observed. Take an electron and fire it toward a barrier with two narrow slits. On the other side, place a detector screen. Where will the electron land? If electrons are particles, each one should go through one slit or the other, creating two bands of hits on the screen. But that's not what happens. Instead, an interference pattern emerges with multiple bands of high and low probability, exactly like waves interfering with each other. The only way to explain this pattern is if each electron somehow passes through both slits simultaneously, interfering with itself on the other side. Fire the electrons one at a time, so slowly that only one is in flight at any moment. The interference pattern still builds up, dot by dot. Each individual electron must be going through both slits. It's not that we don't know which slit it went through. It genuinely goes through both, existing in a superposition of two paths. But place a detector at the slits to determine which one each electron uses. Suddenly, the interference pattern vanishes. Two bands appear, just as you'd expect for particles going through one slit or the other. The act of measurement forces each electron to choose a path. Before observation, it takes both. This is the quantum world laid bare, where particles are not tiny billiard balls following definite trajectories, but something far more mysterious. Every particle has a wavelength, even you, though yours is impossibly small. In 1924, Louis de Broglie proposed something radical. If light waves can behave like particles, then perhaps particles can behave like waves. He suggested that every particle has an associated wavelength, determined by its momentum. The faster something moves, the shorter its wavelength. For everyday objects, this wavelength is far too small to detect. A baseball thrown across a field has a wavelength billions of times smaller than an atomic nucleus. You, walking across a room, have a wavelength trillions of times smaller than that. But for particles as light as electrons, the wavelength can be comparable to the size of atoms. And at that scale, wave behavior becomes impossible to ignore. Electrons passing through crystals create diffraction patterns, just like light waves passing through gratings. This isn't a metaphor or a mathematical trick. Particles genuinely have wavelengths. They spread out. They interfere with themselves. The smaller and lighter the particle, the more pronounced its wave nature becomes. This wave nature is why electrons in atoms don't spiral into the nucleus. They form standing waves around the atom, stable patterns like the harmonics of a vibrating string. Matter, at its most fundamental level, is wave-like. Everything, including you, is a wave in the quantum field. though your wavelength is far too small for the wave nature to manifest in any noticeable way. The double-slit experiment reveals reality's deepest mystery. Observation changes outcome. The double-slit experiment is deceptively simple, yet it encapsulates the most profound mystery of quantum mechanics. Send particles, one at a time, toward two slits. Don't observe which slit each particle uses. An interference pattern emerges on the detector screen, proving each particle went through both slits as a wave. Now, place detectors at the slits to see which path each particle actually takes. The moment you observe, the interference pattern disappears. Two simple bands appear, as if each particle went through one slit, or the other as a definite particle. It's not the physical presence of the detectors causing this change. It's the information gained, the act of observation, of determining which path the particle took, fundamentally alters the outcome. Before observation, the particle exists in a superposition, taking both paths simultaneously. After observation, it has a definite history. You might think there's some hidden mechanism, some subtle disturbance from the detector causing this. But experiments have ruled out all such explanations. The universe genuinely behaves differently depending on whether information is gathered. This isn't a technological limitation or a human perceptual issue. This is nature telling us something strange. Reality at the quantum level is not independent of observation. The very act of looking helps create what you see. Matter waves were predicted mathematically before being observed in experiments. De Broglie's hypothesis that particles have wavelengths was initially met with skepticism. It seemed too strange, too symmetrical, almost poetic rather than physical. But the mathematics was elegant and the reasoning compelling. If wave-particle duality applied to light, why not to matter? Within a few years, experiments confirmed his prediction. In 1927, Clinton Davison and Lester Germer fired electrons at a nickel crystal and observed diffraction patterns, exactly as you'd expect from waves. Around the same time, George Paget Thomson passed electrons through thin metal films and saw similar effects. Electrons, which everyone thought were particles, were creating interference patterns, the unmistakable signature of waves. Later, the same wave behavior was confirmed for atoms, then molecules, even large organic molecules made of dozens or hundreds of atoms. In recent years, experiments have demonstrated the wave nature of molecules so large you can almost see them under a microscope. Each time, the predictions of quantum mechanics held true. The wavelength was always exactly what de Broglie's equation predicted. This is science at its best. A bold theoretical prediction, grounded in elegant reasoning, confirmed by careful experiment, revealing something completely unexpected about the nature of matter itself. You cannot know both a particle's exact position and momentum simultaneously. This is the Heisenberg uncertainty principle, one of the most famous and misunderstood ideas in physics. It's often explained as a measurement problem, as if precise instruments could overcome it. But that's not what it is. The uncertainty isn't about our knowledge or our tools. It's about what exists. A particle doesn't have an exact position and an exact momentum at the same time. These properties are fundamentally blurred. The more precisely you determine where a particle is, the less defined its momentum becomes. Confine an electron to a tiny region, and its momentum becomes wildly uncertain, meaning it could be moving in many different directions with many different speeds. Measure its momentum precisely, and its position spreads out into a fuzzy cloud. This trade-off is built into the mathematics of quantum mechanics, into the very structure of the wave function. Position and momentum are related by a Fourier transform, and localizing a wave in position inherently spreads it out in momentum space. This isn't philosophy. It has real consequences. It's why electrons don't crash into atomic nuclei. Confining them too tightly would give them enormous kinetic energy from the uncertainty principle. It's why we can't predict exactly when a radioactive atom will decay. The universe itself doesn't know until it happens. Uncertainty isn't about measurement limitations, it's built into reality itself. It's tempting to think that particles really do have exact positions and momenta, and we just can't measure them both accurately. But quantum mechanics says no. The universe doesn't contain that information. Before measurement, a particle doesn't have a definite position waiting to be discovered. It has a probability distribution, a spread of possible positions. This isn't ignorance on our part. The particle genuinely doesn't have a single, definite position until something forces it to. The uncertainty principle is a statement about nature, not about human limitations. It emerges from the wave nature of particles. A wave, by its very nature, is spread out. To make a wave more localized in space, you have to add together many waves of different wavelengths, which means different momenta. The more tightly you localize it, the broader the range of wavelengths you need. This is a mathematical fact about waves, and since particles are waves, the same applies to them. Einstein struggled with this for his entire life. He believed there must be some deeper level of reality, some hidden variables that determine everything precisely, and quantum mechanics just didn't have access to them. But experiment after experiment has shown he was wrong. The uncertainty is real. Reality at the quantum level is fundamentally probabilistic, fundamentally uncertain, and there's no deeper deterministic layer beneath it. The more precisely you measure one property, the less you can know about its complement. Position and momentum are what physicists call conjugate variables. They're linked by the uncertainty principle in such a way that improving your knowledge of one degrades your knowledge of the other. This isn't unique to position and momentum. Energy and time are also conjugate variables. Measure the energy of a system with great precision, and the time at which it has that energy becomes uncertain. This allows particles to briefly violate energy conservation, as long as they do it quickly enough that the uncertainty in time allows it. Angular momentum components are conjugate to each other. You can measure one component of a particle's spin precisely, but then the other components become completely uncertain. These trade-offs aren't arbitrary. They emerge from the mathematical structure of quantum mechanics, from the fact that certain operators don't commute. In everyday language, measuring A and then B gives a different result than measuring B and then A. The order matters. This non-commutativity is the deep reason for quantum uncertainty. It's woven into the fabric of quantum theory, and through quantum theory, into the fabric of reality. The universe enforces these relationships. You can't get around them with cleverness or technology. They're as fundamental as the speed of light. Heisenberg's uncertainty principle sets a fundamental limit on knowledge. Werner Heisenberg formulated his uncertainty principle in 1927, and it shook physics to its core. For the first time, a fundamental limit on knowledge was discovered. Not a practical limit, not a technological limit, but a limit imposed by nature itself. You can know the universe only so well. Push to learn one thing precisely, and something else slips away from you. The principle can be written as a simple inequality. The uncertainty in position multiplied by the uncertainty in momentum must be greater than or equal to Planck's constant divided by 4 pi. Planck's constant is tiny, which is why we don't notice quantum uncertainty in everyday life. But at atomic scales, it dominates. This limit isn't just about particles. It applies to light, to fields, to energy and time. It's baked into the structure of quantum field theory, the most fundamental description of nature we have. The uncertainty principle has philosophical implications that physicists still debate. Does it mean the universe is fundamentally indeterministic? Does it mean information is somehow limited at the deepest level? Or does it mean we're asking the wrong questions, trying to impose classical concepts like position and momentum on a reality that doesn't work that way? Whatever the answer, the universe has made one thing clear. There are things we cannot know, not because of our limitations, but because those things don't exist to be known. Uncertainty allows particles to briefly borrow energy from the vacuum of space. One of the strangest consequences of the uncertainty principle involves energy and time. If the uncertainty in time is small, the uncertainty in energy can be large. This means that for very brief moments, particles can have wildly uncertain energy, even borrowing energy from nothing, as long as they pay it back quickly. The vacuum of space is not truly empty. It seethes with these quantum fluctuations. Virtual particles pop into existence in matter. Antimatter pairs borrow energy from the vacuum, exist for a fleeting instant, and then annihilate each other, returning the borrowed energy. The shorter their lifetime, the more energy they can borrow. These aren't just theoretical curiosities. They have measurable effects. They contribute to the mass of particles. They alter the behavior of electromagnetic fields. The Casimir effect, where two metal plates in a vacuum are pushed together by quantum fluctuations, is direct evidence of this. The fluctuations create a pressure. The vacuum has structure, has energy, has activity, all because of the uncertainty principle. In the early universe, quantum fluctuations were stretched by cosmic inflation into the seeds of galaxies. The uncertainty principle, at the beginning of time, sculpted the large-scale structure of everything you see in the night sky. Something from nothing, allowed by the strange rules of the quantum world. A quantum particle exists in all possible states simultaneously until measured. Imagine an electron orbiting an atom. Before you measure its position, it's not at some specific location that you just don't happen to know. It's in a superposition, genuinely spread out in a cloud of probability around the nucleus. It exists in all possible positions simultaneously. The wave function describing the electron contains all these possibilities, each with a certain amplitude, a certain probability. The electron is not secretly in one place, and you're just ignorant of which. It's in all of them. This is superposition, one of the most counterintuitive ideas in quantum mechanics. A particle in a superposition isn't flickering rapidly between states. It's not in one state part of the time and another state another part of the time. It's genuinely in multiple states at once, occupying a kind of existence that has no analog in our everyday experience. When you measure the electron's position, the superposition collapses. All the possibilities vanish except one. The electron is found at a specific location, but before measurement, it wasn't there. It was everywhere the wave function said it could be. This isn't a failure of knowledge. It's the way quantum systems exist. Superposition is real, confirmed by countless experiments, and it's the foundation of quantum computing, quantum cryptography, and much of modern physics. Schrödinger's cat thought experiment illustrates superposition's strangeness. Erwin Schrödinger, one of the founders of quantum mechanics, proposed a thought experiment to show how absurd quantum superposition seems when applied to everyday objects. Imagine a cat in a sealed box. Inside the box is a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers, breaking the vial and killing the cat. Radioactive decay is a quantum process. Until you observe it, the atom is in a superposition of decayed and not decayed states. According to quantum mechanics, this means the cat is in a superposition of alive and dead. Not alive or dead, but both simultaneously. Only when you open the box and observe does the superposition collapse, and the cat becomes definitely alive or definitely dead. Schrödinger didn't propose this to celebrate quantum mechanics. He was showing what he saw as an absurdity, trying to highlight that something must be wrong with applying quantum rules to large objects. But experiments in recent decades have created superpositions of larger and larger systems, not cats yet, but molecules, photons in multiple places at once, even small mechanical oscillators. The line between quantum and classical is blurrier than Schrödinger imagined. The cat thought experiment endures because it captures the weirdness of quantum mechanics in a visceral, unforgettable way. Superposition collapses instantly when a quantum system interacts with the larger world. Superposition is fragile. A quantum system can exist in multiple states simultaneously as long as it remains isolated from its environment. But the moment it interacts with the outside world, with air molecules, stray photons, thermal vibrations, anything at all, the superposition collapses. This process is called decoherence. It's why you don't see superpositions in everyday life. Each interaction leaks information about the quantum system into the environment, and once that information is out there, spread across countless particles, the coherence is lost. The system transitions from behaving quantum mechanically to behaving classically. Decoherence explains why we don't see superpositions in everyday life. A baseball thrown through the air is interacting with trillions of air molecules, each one causing a tiny bit of decoherence. Within an unimaginably short time, any quantum behavior the baseball might have had is gone. It behaves classically. Only carefully isolated systems, like single atoms in ultra-high vacuum chambers, cooled to near absolute zero, can maintain quantum coherence long enough to observe. Decoherence is not wave function collapse, at least not exactly, but it produces something that looks like collapse. The system appears to be in one definite state because the superposition has been washed out by environmental interaction. Quantum computers use superposition to process multiple calculations at once. A classical computer processes information using bits, each of which is either a 0 or a 1. A quantum computer uses qubits, quantum bits, which can be in a superposition of both 0 and 1 simultaneously. With 2 qubits, you can be in a superposition of 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. 3 qubits give you 8 states. The number of states grows exponentially. With just 300 qubits, you could be in a superposition of more states than there are atoms in the observable universe. This allows quantum computers to explore a vast number of possibilities in parallel. A quantum algorithm manipulates the superposition so that wrong answers cancel out through interference, and the right answer is amplified. When you measure the qubits at the end, the superposition collapses, and you read out the result. Quantum computers won't replace classical computers for everyday tasks, but for certain problems, factoring large numbers, simulating quantum systems, searching databases, they offer exponential speedups. The challenge is maintaining the superposition long enough to complete the calculation. Decoherence is the enemy, constantly threatening to collapse the qubits before the algorithm finishes. Building large, stable quantum computers is one of the great engineering challenges of our time. But the principle is proven. Superposition, that strange quantum phenomenon, can be harnessed to compute in ways no classical computer ever could. Atoms can be in 2 places at the same time in carefully controlled conditions. It sounds impossible, but experiments have placed atoms in spatial superpositions, existing in 2 locations simultaneously. In 1991, researchers used an interferometer to put beryllium ions in a superposition of being in 2 places about 80 nanometers apart. That's a tiny distance, but it's enormous compared to the size of an atom. The atoms were in both locations at once, not moving between them, not flickering, but genuinely occupying both positions as a quantum superposition. Later experiments extended this to larger molecules and greater separations. In 2019, physicists created a superposition of a molecule made of 2,000 atoms, split across space. The molecule was in two places simultaneously, separated by a distance comparable to its own size. These experiments require extraordinary precision. The systems must be isolated from the environment to prevent decoherence. Any interaction with a stray photon or air molecule would collapse the superposition. But under the right conditions, matter can exist in two places at once, just as quantum mechanics predicts. This isn't science fiction or metaphor. It's been done, measured, and confirmed. The quantum world is not a theory or an approximation. It's the way reality works, even if it defies every intuition we have about how things should behave. Two particles can become connected so deeply that distance becomes meaningless. Quantum entanglement is perhaps the strangest prediction of quantum mechanics, and experiments have confirmed it beyond doubt. When two particles interact in certain ways, they become entangled. Their properties become correlated, not in a simple statistical sense, but in a deep quantum way. Measure a property of one particle, and you instantly know the corresponding property of the other, no matter how far apart they are. If two electrons are entangled in their spin states, measuring one as spin up means the other is spin down, even if it's on the other side of the galaxy. The particles don't have definite spins before measurement. They're both in a superposition. But the superposition is shared. They're described by a single wave function that links them. When you measure one, you collapse the wave function for both, and the results are perfectly correlated. This correlation is stronger than anything possible in classical physics. It's not that the particles agreed ahead of time what their spins would be. The measurement of one genuinely affects the state of the other, instantaneously, regardless of distance. Entanglement is now used in quantum computing, quantum cryptography, and quantum teleportation. It's a real phenomenon, a fundamental feature of quantum mechanics, and it tells us that the universe is far more interconnected than we ever imagined. Einstein called entanglement spooky action at a distance, and he was skeptical. Albert Einstein never fully accepted quantum mechanics, and entanglement was one of his main objections. In 1935, he and his colleagues Boris Podolsky and Nathan Rosen published a paper arguing that quantum mechanics must be incomplete. They described a thought experiment, now called the EPR paradox, showing that if quantum mechanics were correct, measuring one particle would instantaneously affect another particle far away. Einstein found this absurd. He called it spooky action at a distance. He believed that nothing could travel faster than light, including information or influence. He thought there must be hidden variables, properties the particles carried with them that predetermined the outcomes of measurements, making the apparent instantaneous connection an illusion. For decades, this remained a philosophical debate. Then, in 1964, physicist John Bell devised a way to test it. Bell's theorem showed that if hidden variables existed, certain statistical correlations in experiments would be limited. If quantum mechanics were right, the correlations would be stronger. Experiments starting in the 1970s and becoming increasingly sophisticated over the decades consistently sided with quantum mechanics. The correlations were exactly as strong as quantum mechanics predicted, ruling out local hidden variable theories. Einstein was wrong. Entanglement is real. The universe does have spooky action at a distance, though it doesn't allow faster than light communication. The connection is real, and it's strange beyond what even Einstein could accept. Measuring one entangled particle instantly affects its partner, even light years away. Once two particles are entangled, they form a single quantum system. They're not two separate things anymore, at least not in the way you'd think. The wave function describing them is a joint wave function, a single mathematical object that encompasses both particles. When you measure one particle, you gain information about the system, and that information is instantly reflected in the state of the other particle, no matter how far away it is. If two entangled photons are separated by a light year, measuring the polarization of one immediately determines the polarization of the other. There's no signal traveling between them. The effect is instantaneous. This has been tested in experiments where the measurements are made so quickly that no signal traveling at the speed of light could connect them. The correlation still appears. Somehow, the universe updates the state of both particles simultaneously. This doesn't violate relativity because you can't use entanglement to send information faster than light. The measurement results on each side are random. Only when you bring the results together and compare them do you see the correlation. But the correlation itself is spooky. It suggests that space, at the quantum level, is not what it seems. Distance may not separate particles as completely as we think. Entanglement hints at a deeper level of reality, where everything is connected in ways we're only beginning to understand. Entanglement doesn't allow faster than light communication despite the instant connection. It's tempting to think that entanglement could be used to send messages faster than light. After all, measuring one particle instantly affects the other, even across vast distances. But there's a catch. The outcomes of measurements on entangled particles are random. You can't control what result you get. If you measure the spin of one entangled electron, you get spin up or spin down randomly. You can't force it to be one or the other. The person measuring the other electron also gets a random result. Only when you compare your results, using ordinary slower than light communication, do you see the correlation. There's no way to encode a message in the measurement results because you don't control the results. The randomness ensures that no information is transmitted faster than light. Entanglement provides correlation, not communication. This preserves the principle that no information or influence can travel faster than light, which is a cornerstone of relativity. Quantum mechanics and relativity are compatible, though the fit is subtle and sometimes uncomfortable. Entanglement shows us that the universe can have non-local correlations, strange connections that don't rely on signals traveling through space, while still respecting the cosmic speed limit. It's one more way the quantum world is stranger and more sophisticated than the world we see. Entangled particles have been separated by hundreds of kilometers and still remain connected. Entanglement is not just a laboratory curiosity confined to microscopic distances. Experiments have entangled photons and then separated them by hundreds of kilometers using fiber optic cables or even open air and satellites. In 2017, China's Maisha satellite created entangled photons in orbit and sent them down to ground stations separated by over 1,200 kilometers. The entanglement survived. Measurements on the two photons remained perfectly correlated, despite the enormous distance and the photons traveling through Earth's atmosphere. This experiment proved that entanglement is robust enough to work on truly macroscopic scales, opening the door to global quantum communication networks. Other experiments have entangled particles and stored one of them in a quantum memory for hours or even days, while the other is measured immediately. The entanglement persists across time as well as space. The connection between entangled particles is not fragile or fleeting. It's a genuine feature of how quantum systems exist. As technology improves, entanglement will become a practical tool for secure communication, distributed quantum computing, and perhaps even tests of quantum mechanics over even greater distances. The quantum world is not hidden away in laboratories. It extends across space and time, connecting particles in ways that challenge our understanding of what connection even means. Empty space isn't truly empty. It seethes with virtual particles constantly appearing and vanishing. The quantum vacuum is not a void. It's a restless sea of activity, with particle-antiparticle pairs constantly flickering into existence and annihilating each other almost immediately. These are called virtual particles, and they arise from quantum fluctuations. The uncertainty principle allows energy to be borrowed from the vacuum, as long as it's paid back quickly. An electron and a positron can pop into existence, exist for a tiny fraction of a second, and then annihilate, returning the energy. These virtual particles are not directly observable, but their effects are measurable. They alter the energy levels of atoms. They contribute to the masses of particles. They affect the way charged particles interact. Virtual particles are constantly appearing around every electron, every proton, every quantum field in the universe. The vacuum is alive with this quantum foam, a frothing sea of particles that never quite solidify into reality, but influence everything nonetheless. This isn't speculation. Quantum field theory, which incorporates virtual particles, makes predictions accurate to 10 decimal places. The vacuum has structure, and that structure matters. Space is not a passive stage on which particles move. It's an active participant in the quantum dance, filled with potential, with energy, with ghosts of particles that almost exist. The vacuum has measurable energy that can push metal plates together. In 1948, Dutch physicist Hendrik Casimir predicted a strange effect based on the quantum vacuum. If you place two uncharged metal plates very close together in a vacuum, they should attract each other. Not because of gravity or magnetism, but because of the quantum fluctuations of empty space. The reasoning is subtle. Virtual particles appear and vanish everywhere in the vacuum, creating a kind of pressure. But between the plates, only virtual particles with certain wavelengths can exist, those that fit between the plates. Outside the plates, all wavelengths are allowed. This creates an imbalance. There are slightly more virtual particles pushing on the outside of the plates than on the inside. The result is a net force pushing the plates together. This is the Casimir effect, and it's been measured. Experiments have placed metal plates nanometers apart and detected the attractive force, exactly as Casimir predicted. The vacuum is not just a theoretical concept. It has measurable, physical consequences. It can push on matter. This effect is tiny for everyday objects, but at microscopic scales, it becomes important. Engineers designing nanomachines must account for the Casimir force. The vacuum, this supposedly empty nothing, is full of something real enough to move metal. Quantum fluctuations in the early universe became the seeds of galaxies. In the first moments after the Big Bang, the universe was incredibly small, dense, and hot. Quantum fluctuations, the same random variations that create virtual particles in the vacuum today, were everywhere. But then, cosmic inflation occurred. The universe expanded exponentially, faster than the speed of light, stretching space itself. Those tiny quantum fluctuations were stretched along with space. Subatomic variations became fluctuations the size of planets, then stars, then galaxies. When inflation ended and the universe continued expanding at a more sedate pace, those stretched quantum fluctuations became density variations. Some regions had slightly more matter, some slightly less. Gravity amplified these differences. Denser regions attracted more matter, growing into the first stars, galaxies, and clusters. The large-scale structure of the universe, the cosmic web of filaments and voids, all traces back to quantum fluctuations in the first fraction of a second. Tiny, random quantum events, magnified to cosmic scales by inflation, shaped everything you see in the night sky. The uncertainty principle, operating at the Planck scale, sculpted the universe across billions of light years. you exist because of quantum mechanics. The Earth, the Sun, the Milky Way, all of it arose from quantum uncertainty at the beginning of time. The Casimir effect proves the quantum vacuum exerts real physical force. The Casimir effect is one of the most direct confirmations that the quantum vacuum is not merely a theoretical abstraction. In a series of increasingly precise experiments over decades, physicists have measured the force between uncharged metal plates in a vacuum and found it matches the predictions of quantum field theory. The force is tiny, about 1/10 of a billionth of a newton for plates a micrometer apart, but it's measurable. More impressively, the force depends on the geometry of the plates and their material properties in exactly the way quantum mechanics predicts. Experiments have used different shapes, different materials, different separations, and every time, the Casimir effect behaves as expected. This force arises purely from the quantum structure of the vacuum, from the zero-point energy of electromagnetic fields. Even at absolute zero, where classical physics says all motion should stop, quantum fields still fluctuate. Those fluctuations have energy, and that energy can do work. The Casimir effect is proof. The vacuum is not empty. It's filled with fields in their ground state, and those fields push on matter. At the nanoscale, this effect becomes important for engineering. At the cosmic scale, it connects to dark energy and the expansion of the universe. The quantum vacuum is everywhere, pressing gently on everything, a whisper of energy in the spaces between. Virtual particles can briefly violate energy conservation before disappearing back into nothing. In classical physics, energy conservation is absolute. Energy cannot be created or destroyed. But in quantum mechanics, the uncertainty principle allows temporary violations. If the time interval is short enough, the uncertainty in energy can be large. This means particles can borrow energy from the vacuum, appear briefly, and then vanish, paying the energy back. The shorter their existence, the more energy they can borrow. This is how virtual particles work. They pop into existence, violate energy conservation for a fleeting instant, and then disappear. These violations are not detectable directly because they happen too quickly, but they have consequences. Virtual particles surround every real particle, screening its charge, altering its apparent mass, changing how it interacts. They mediate forces. The electromagnetic force, for example, is carried by virtual photons. An electron repels another electron by exchanging virtual photons that carry momentum between them. These photons don't last long enough to be observed directly, but they're the mechanism of the force. The strong nuclear force is mediated by virtual gluons, the weak force by virtual W and Z bosons. Forces, at the quantum level, are interactions mediated by particles that don't quite exist. The universe operates on a kind of quantum credit system, constantly borrowing and repaying energy, maintaining the balance on average while allowing wild fluctuations at every instant. Particles can pass through barriers they shouldn't have enough energy to cross. Imagine rolling a ball up a hill. If it doesn't have enough energy to reach the top, it rolls back down. But in quantum mechanics, particles can sometimes pass through barriers even when they don't have enough energy to go over them. This is quantum tunneling. A particle approaching a barrier isn't a tiny billiard ball. It's a wave function, a cloud of probability. Most of that wave function reflects off the barrier, but a small part leaks through to the other side. If the barrier is thin enough, there's a non-zero probability that the particle will be found on the far side, having tunneled through. It didn't climb over. It didn't smash through. It just appeared on the other side because its wave function extended through the barrier. Tunneling probability decreases rapidly with barrier thickness and increases with the energy of the particle. For large objects, the probability is so small that tunneling never happens. But for electrons, protons, and other light particles, tunneling is common. It's not a rare curiosity. It's a fundamental aspect of how quantum particles behave. Tunneling is why alpha particles can escape from atomic nuclei in radioactive decay. It's why the sun shines. It's why your electronic devices work. Barriers that seem impenetrable in classical physics are, in the quantum world, permeable. The sun shines because of quantum tunneling allowing fusion to occur. The sun generates energy by fusing hydrogen into helium in its core. For fusion to occur, hydrogen nuclei, which are just protons, must be brought close enough together that the strong nuclear force can bind them. But protons repel each other electrically. They're both positively charged. To overcome this repulsion and get close enough to fuse, they need enormous energy. At the temperature in the sun's core, about 15 million degrees, protons are moving fast, but not fast enough. Classical physics says fusion shouldn't happen at that temperature. The protons don't have enough energy to overcome the electric repulsion, but quantum mechanics says otherwise. The protons, being quantum particles, have wave functions that extend beyond their classical positions. There's a small probability that two protons will quantum tunnel through the electric barrier separating them, appearing close enough together for the strong force to take over and fuse them. This probability is tiny for any given pair of protons, but the sun's core contains an unimaginable number of protons colliding constantly. Even a tiny probability, multiplied by countless attempts every second, produces enough fusion to power the sun. Without quantum tunneling, stars wouldn't shine. The universe would be cold and dark. Life wouldn't exist. The warmth of sunlight on your face is a consequence of quantum mechanics operating at the heart of the sun. Tunneling happens because particles exist as probability clouds, not solid objects. Quantum tunneling is only possible because particles are not hard, localized objects. An electron is not a tiny sphere sitting at a definite point in space. It's described by a wave function, a mathematical object that gives the probability of finding the electron at each location. The wave function spreads out. Even if most of the wave function is on one side of a barrier, a small part extends through and beyond the barrier. This means there's a probability, however small, that the electron will be detected on the other side. The electron doesn't have to cross the barrier. It doesn't drill a hole. It simply exists with some probability on both sides, and upon measurement, it might be found to have tunneled through. This is deeply strange. It means position is not a definite property particles have at all times. Position is something that emerges upon measurement. Before measurement, the particle is spread out, existing in a superposition of many locations. Tunneling is a natural consequence of this wave nature. In a sense, the particle doesn't go through the barrier. It was never localized enough to be strictly on one side or the other. Its wave function always extended through, and sometimes, when measured, the particle is found on the far side. Tunneling is not an exception to the rules of quantum mechanics. It's a direct expression of them. Your electronic devices rely on quantum tunneling to function. The transistors inside your computer, your phone, every modern electronic device, operate because of quantum tunneling. A transistor is a switch that controls the flow of electric current. In modern devices, transistors are incredibly small, with features just a few nanometers across. At these scales, quantum effects dominate. Electrons can tunnel through the thin barriers inside the transistor, allowing current to flow even when classical physics says it shouldn't. Engineers design transistors to exploit tunneling, using it to control current flow with precision. Flash memory, the storage in USB drives and solid-state hard drives, also relies on tunneling. Data is stored as electric charge trapped in tiny cells. Electrons tunnel in and out of these cells to write and erase data. Without quantum tunneling, flash memory wouldn't work. As transistors shrink, tunneling becomes both a tool and a challenge. At some point, they become so small that unwanted tunneling causes errors. Electrons tunnel where they shouldn't, and the device stops working reliably. This is one of the limits to how small transistors can get. But for now, tunneling is harnessed brilliantly, enabling the technology you use every day. Your ability to read these words, to communicate instantly with anyone on Earth, to carry vast libraries in your pocket. All of it depends on quantum mechanics and the strange behavior of particles at the smallest scales. Tunneling allows particles to be on the other side of a wall without ever traveling through it. This is one of the most counterintuitive aspects of quantum tunneling. A particle doesn't travel through the barrier. It doesn't spend time inside the barrier moving from one side to the other. In fact, asking where the particle was during the tunneling event doesn't make sense. The particle's wave function extends through the barrier. Before measurement, the particle is in a superposition, simultaneously on both sides and inside the barrier. When a measurement is made, the wave function collapses, and the particle is found in one location. Sometimes it's on the near side, reflected. Sometimes it's on the far side, tunneled. But it didn't take a path from one side to the other. There's no journey. This violates our intuitive sense of motion and position, but it's consistent with quantum mechanics. Particles don't have continuous trajectories at the quantum level. They don't move smoothly from point A to point B. Position is something that only has meaning when measured. Between measurements, the particle is described by a wave function, and the wave function can extend across barriers, through walls, across seemingly impossible divides. Tunneling is not a particle sneaking through a crack. It's a particle being found on the other side because its quantum nature allows it to be in multiple places at once. And sometimes, the universe chooses the far side. The act of observation fundamentally changes what is being observed. This is not about the observer disturbing the system with clumsy instruments. In quantum mechanics, observation has a deeper, stranger role. Before observation, a quantum system exists in a superposition of states. The wave function contains multiple possibilities. When an observation is made, the superposition collapses to a single outcome. The system is no longer in a superposition. It has a definite state. This collapse is not a physical process like a wave crashing on a shore. It's a discontinuous change in the mathematical description of the system. One moment, the system is in multiple states. The next, it's in one. What counts as an observation? This is the measurement problem, one of the deepest unsolved questions in quantum mechanics. Is it the physical interaction with a measuring device? Is it the recording of information? Is it conscious awareness? No one knows for sure. Experiments have ruled out some possibilities and confirmed others, but the fundamental question remains open. What we do know is that observation changes things. Not because we're bad at observing, but because observation is part of the process by which quantum possibilities become classical realities. The universe doesn't contain definite outcomes waiting to be revealed. It contains probabilities, and observation is the event that selects one outcome from the spectrum of possibilities. Before measurement, quantum systems exist in a haze of probability. A particle before measurement is not in one state that we just don't know. It's in all possible states at once, each with a certain probability. The wave function encodes this information, assigning an amplitude to each possible state. The square of that amplitude gives the probability of finding the system in that state upon measurement. Until measurement, the particle is smeared out across all these possibilities. An electron in an atom isn't orbiting at a fixed distance. It's in a cloud, present everywhere the wave function allows, all at once. A photon traveling through space doesn't have a definite position. It's spread out, existing everywhere along its path as a wave of probability. This probabilistic existence is not ignorance. It's reality. The particle genuinely doesn't have a definite position. The universe doesn't know where it is because it isn't anywhere specific. Only when you measure does the universe choose. The wave function collapses. All the possibilities vanish except one. The particle is found at a location with a momentum in a state. But that state didn't exist before measurement. It was created by the measurement. This is quantum mechanics laid bare, reality emerging from probability, and the role of observation in creating the world we experience. No one fully understands what counts as observation in quantum mechanics. The measurement problem is one of the greatest unsolved puzzles in physics. Quantum mechanics tells us that observation causes wave function collapse, but it doesn't define what observation is. Does a measuring device count, even if no human looks at the result? Does the interaction have to be irreversible, recording information permanently? Does consciousness play a role, as some interpretations suggest? Experiments have probed these questions. Delayed choice experiments show that the decision to observe can be made after the particle has already passed through the apparatus. Yet the outcome changes as if the particle knew what was coming. Quantum eraser experiments show that erasing information can restore interference patterns that observation destroyed. These results deepen the mystery rather than solving it. Most physicists today think decoherence, the interaction with the environment, plays a key role. A quantum system interacting with many degrees of freedom in the environment effectively measures itself, causing apparent collapse without any human observer. But this doesn't fully solve the problem. It explains why superpositions vanish for large systems, but it doesn't explain the single definite outcome of each measurement. The measurement problem remains, a crack in the foundation of quantum mechanics, a place where the theory is silent about what really happens. Measurement forces reality to choose one outcome from many possibilities. Before you measure, a quantum system exists in a superposition. Many outcomes are possible, and the wave function assigns a probability to each. When you measure, the system is found in one of those outcomes. The others disappear. This is wave function collapse. The system goes from being in many states simultaneously to being in one definite state. The collapse is instantaneous and discontinuous. There's no gradual transition. The wave function simply jumps from a superposition to a single state. Which state is chosen? That's determined by probability. If the wave function gives a 70% probability for one outcome and 30% for another, repeated measurements will find the first outcome about 70% of the time and the second about 30% of the time. But for any single measurement, the result is random. Quantum mechanics can predict the probabilities, but it cannot predict the outcome of an individual measurement. This randomness is fundamental, not a reflection of hidden ignorance. The universe itself doesn't know which outcome will occur until the measurement happens. Collapse is the moment when potential becomes actual, when the quantum world interfaces with the classical world, when the many become one. It's a moment of creation, of reality coming into being, and it happens every time a measurement is made, countless times per second, everywhere in the universe. The measurement problem remains one of physics' deepest philosophical questions. Despite the success of quantum mechanics, despite its incredible predictive power, physicists do not agree on what the theory means. The measurement problem is at the heart of this disagreement. If the wave function is a complete description of reality, why does it collapse? What causes collapse? Is collapse even real, or is it just an approximation? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation says the wave function is just a tool for predicting measurement outcomes, not a description of objective reality. Many worlds says the wave function never collapses. All outcomes happen, each in a different branch of the universe. Pilot wave theory says particles have definite positions guided by a wave, and collapse is an illusion. Each interpretation has strengths and weaknesses. Each raises new questions. No experiment has definitively ruled out any major interpretation. The mathematics of quantum mechanics is unambiguous and works perfectly. But what that mathematics tells us about reality remains controversial. Some physicists think this is a philosophical question, not a scientific one. Others believe future experiments or theoretical breakthroughs will resolve it. For now, the measurement problem stands as a reminder that our most successful scientific theory is also, in some ways, deeply mysterious. Electrons spin, but not in the way anything spins in our everyday world. When physicists say an electron has spin, they don't mean it's rotating like a planet or a top. Spin is an intrinsic property of quantum particles, a kind of angular momentum that has no classical analog. An electron has spin even though it's not spinning. The name is historical, a remnant from early attempts to understand what experiments were revealing. Electrons behave as if they have angular momentum, as if they're rotating, but they're not. Spin is a quantum property, something that simply exists as part of what an electron is. Every electron has the same amount of spin, a fixed value that never changes. Spin comes in units of half of Planck's constant divided by 2 pi. Electrons, protons, and neutrons are spin 1/2 particles. Photons are spin 1. The Higgs boson is spin 0. Hypothetical gravitons would be spin 2. Spin affects how particles behave, how they interact, and what quantum states they can occupy. It's one of the fundamental properties that define a particle as intrinsic as mass or charge. But unlike mass or charge, spin doesn't have an everyday equivalent. It's purely quantum, a feature of reality that only makes sense in the quantum framework. Spin is an intrinsic quantum property with no classical analog. You might think spin is like a tiny gyroscope, an electron rotating on its axis. But that picture doesn't work. If an electron were a classical spinning sphere with the angular momentum it has, the surface would be moving faster than the speed of light, which is impossible. Experiments also show that electrons are point particles, with no measurable size. What would be spinning if there's no extended structure? Spin is intrinsic. It's not caused by motion or rotation. It's a property the particle simply has, like charge. You can't spin an electron up or slow it down. Its spin is fixed. What you can change is the direction of the spin, whether it's pointing up or down relative to some axis. And here's where it gets strange. Before you measure spin, the electron is in a superposition of spin up and spin down. The measurement forces it to choose a direction. Spin is also quantized. It comes in discrete values. You can't have an electron with a little more or a little less spin. It always has the same magnitude. This discreteness, combined with the fact that spin has no classical counterpart, makes it one of the purest expressions of quantum mechanics. Spin is quantum through and through. A particle must rotate 720 degrees to return to its starting configuration. This is one of the strangest properties of spin 1/2 particles like electrons. In classical physics, if you rotate something 360 degrees, it returns to exactly the same state. But for an electron, a 360-degree rotation changes the sign of its wave function. The electron's physical state is the same, but the wave function, which describes the electron, has picked up a minus sign. To return the wave function to its original form, you need to rotate the electron 720 degrees, 2 full turns. This isn't just a mathematical oddity. It has physical consequences. It affects how particles behave under rotations, how they combine into larger systems, how they interfere. Experiments have tested this. Neutrons, which are also spin 1/2, have been passed through interferometers while being rotated. The interference pattern shifts in exactly the way predicted by the 720-degree symmetry. This property is connected to deep mathematics, to the structure of quantum mechanics, and the nature of rotations in three-dimensional space. Particles with spin 1/2 live in a strange geometric world where a full turn is not enough. You have to go around twice to come back to where you started. It's a reminder that the quantum world doesn't just follow different rules. It inhabits a different kind of space, one where intuition fails and mathematics becomes the only guide. Spin comes in discrete values, never in between. In classical physics, angular momentum can have any value. A spinning wheel can rotate at any speed. But in quantum mechanics, spin is quantized. Particles can have spin 0, spin 1/2, spin 1, spin 3/2, and so on in units of Planck's constant divided by 2π. There are no particles with spin 0.3 or spin 0.7. The values are discrete, jumps on a ladder, not points on a continuum. Electrons, protons, and neutrons have spin 1/2. Photons have spin 1. Gravitons, if they exist, have spin 2. The Higgs boson has spin 0. Each type of particle has a fixed spin that never changes. When you measure the spin of an electron along a particular axis, you get one of two results: spin up or spin down, corresponding to +1/2 or -1/2 in units of h-bar. You never get a result in between. If you measure along a different axis, you still get up or down along that axis. The spin vector seems to always align or anti-align with your measurement axis. This quantization is fundamental. It emerges from the mathematics of angular momentum in quantum mechanics. The universe allows only certain discrete values, and particles obey this constraint absolutely. Spin is not a continuous variable. It's a ladder, and particles stand only on the rungs, never in the spaces between. The Stern-Gerlach experiment revealed spin by splitting silver atoms into two paths. In 1922, Otto Stern and Walther Gerlach performed an experiment that would become one of the foundational demonstrations of quantum mechanics. They heated silver until it vaporized, creating a beam of silver atoms. They passed this beam through a magnetic field that varied in strength across space. Classical physics predicted that atoms with magnetic moments would deflect by different amounts depending on their orientation, creating a spread-out pattern on a detector screen. But that's not what happened. The beam split into two distinct spots. The atoms went either up or down, with no atoms landing in between. This was the first direct evidence of quantum spin. Silver atoms have a single unpaired electron in their outer shell, giving them a net magnetic moment from that electron's spin. When the atoms passed through the magnetic field, the spin interacted with the field, deflecting the atoms. But because spin is quantized, only two outcomes were possible: spin up or spin down. The beam split cleanly in two, no intermediate values. This experiment showed that angular momentum is quantized, that spin comes in discrete units, and that measurement forces a quantum system to choose one definite state. The Stern-Gerlach experiment is still taught today because it captures, in a simple and direct way, the quantum nature of the world. Quantum mechanics deals in probabilities, not certainties. In classical physics, if you know the initial conditions of a system precisely, you can predict its future precisely. Quantum mechanics doesn't work that way. Even with perfect knowledge of a system, you can only predict the probabilities of different outcomes. The wave function gives you the probability amplitude for each possible result. Square the amplitude, and you get the probability. But the outcome of any single measurement is random. Send a photon through a half-silvered mirror. It has a 50% chance of passing through and a 50% chance of reflecting. You cannot predict what an individual photon will do. Run the experiment 1,000 times, and about half will pass and half will reflect. But each individual outcome is uncertain. This uncertainty is not due to ignorance or hidden variables. It's intrinsic to the quantum world. The universe itself doesn't know what will happen until it happens. Einstein hated this. He believed in a deterministic universe where everything unfolds according to fixed laws. But experiment after experiment has confirmed that quantum mechanics is correct. Probability is not a temporary placeholder for deeper knowledge. It's the deepest level there is. The future is not determined. It's a spectrum of possibilities, and only when the moment arrives does one possibility become real. Radioactive decay is truly random, impossible to predict for individual atoms. Radioactive atoms decay, emitting particles and transforming into different elements. A sample of carbon-14, for example, has a half-life of about 5730 years, meaning that after that time, half the atoms will have decayed. This is a statistical property. For a large number of atoms, you can predict with great accuracy how many will decay in a given time. But for any single atom, you cannot predict when it will decay. It might decay in the next second, or the next million years. There's no clock inside the atom counting down. There's no hidden mechanism determining the moment of decay. It's truly random. Quantum mechanics gives the probability of decay per unit time, but the actual moment is unpredictable. This randomness has been tested extensively. Physicists have watched individual radioactive atoms and found no pattern, no predictability. The decay is as random as anything can be. This challenges the notion of causality. If an atom decays at a certain moment, what caused it to decay then rather than a second earlier or later? Quantum mechanics says there is no cause. The decay simply happens. Probability becomes the fundamental law. This was deeply disturbing to many physicists, but it's the way the quantum world works. Some events have no cause, no reason, no explanation beyond the roll of quantum dice. The wave function gives the probability of finding a particle in each location. The wave function is the central object in quantum mechanics. It's a mathematical function that encodes everything knowable about a quantum system. For a single particle, the wave function assigns a complex number to each point in space. The square of the absolute value of that number gives the probability of finding the particle at that location if you measure it. If the wave function is large in one region and small in another, the particle is more likely to be found in the first region. But before measurement, the particle isn't in any one place. It's spread out, existing in a superposition of all locations with non-zero probability. The wave function is that superposition. It evolves over time according to the Schrödinger equation, a smooth, deterministic equation. But when you measure, the wave function collapses. All the probabilities vanish except one, and the particle is found at a definite location. The wave function is not just a mathematical tool. Many physicists believe it represents something real, the actual state of the particle. Others think it's just a bookkeeping device for predicting measurements. Either way, the wave function is the key to quantum mechanics, the bridge between the abstract mathematics and the experimental results, the object that captures the probabilistic, uncertain nature of the quantum world. Einstein resisted quantum randomness, insisting God does not play dice. Albert Einstein never fully accepted quantum mechanics, and his objections focused on its randomness and its apparent abandonment of causality. In a letter to Max Born in 1926, he wrote, "God does not play dice with the universe." He believed that quantum mechanics was incomplete, that beneath the probabilities lay a deeper, deterministic reality. He thought there must be hidden variables, properties we can't measure yet that determine outcomes in advance. The randomness, he argued, was just ignorance of these hidden variables. Einstein spent decades trying to find flaws in quantum mechanics, proposing thought experiments to show it led to contradictions or absurdities. His debates with Niels Bohr became legendary. But each time, quantum mechanics survived scrutiny. Bohr found answers to Einstein's challenges. Later, experiments ruled out local hidden variable theories through tests of Bell's inequalities. The universe really is random at the quantum level. There are no hidden variables directing outcomes behind the scenes. Einstein's intuition, as brilliant as it was wrong about this. The dice are fundamental. God, if you want to use Einstein's metaphor, does play dice. Quantum mechanics is not incomplete. It's complete and correct, and the randomness is real. The universe is stranger than even Einstein wanted to believe. Quantum randomness appears to be fundamental, not just hidden ignorance. For decades, physicists debated whether quantum randomness was fundamental or just apparent. Maybe particles really do have definite positions and momenta, and quantum mechanics simply doesn't have access to that information. Maybe there are hidden variables, properties we can't measure, that determine everything in advance. In 1964, John Bell proved that if hidden variables exist, they must obey certain inequalities in experiments involving entangled particles. The correlations between measurements should be limited in specific ways. But if quantum mechanics is correct, those correlations should be stronger. This gave experimentalists a way to test the question. Starting in the 1970s and continuing with increasing sophistication, experiments tested Bell's inequalities. Every time, the results sided with quantum mechanics. The correlations were too strong for hidden variables. Later experiments closed loopholes, ensuring that no signal could travel between measurement sites, that detections were fair, that the settings were chosen randomly. Every test confirmed quantum mechanics. The randomness is real. There are no hidden variables determining outcomes in advance. The universe, at its most fundamental level, is probabilistic. Outcomes are not predetermined. The future is genuinely open, a cloud of possibilities that crystallize into reality only when measured. This is one of the most profound conclusions of modern physics. Randomness is not ignorance. It's the nature of existence. Particles are excitations, ripples, in underlying quantum fields. Quantum field theory is the framework that combines quantum mechanics with special relativity. And it describes the universe not as particles moving through space, but as fields filling all of space. For every type of particle, there's a corresponding field. There's an electron field, a photon field, a quark field, and so on. These fields are everywhere, permeating every point in space, even empty space. A particle is not a separate object sitting in the field. A particle is an excitation of the field, a ripple, a localized disturbance. When you detect an electron, you're detecting a vibration in the electron field. When a photon is emitted, the electromagnetic field gets excited, and that excitation propagates through space as light. The fields are the fundamental objects. Particles are what we observe when we interact with the fields. This changes how we think about creation and annihilation. Particles aren't created from nothing. The field was always there. The particle is just the field vibrating. When a particle is annihilated, the field stops vibrating. The energy goes elsewhere, but the field remains. This picture resolves many puzzles. It explains why all electrons are identical. They're all excitations of the same electron field. It explains particle-antiparticle creation. Exciting the field in one way gives a particle, in another way gives an antiparticle. Quantum field theory is the deepest description of nature we have. Every type of particle has its own field permeating all of space. You are sitting right now in a vast ocean of quantum fields. The electron field is there, the photon field, the quark fields, the Higgs field. They overlap, coexist, fill every cubic centimeter of space. Most of the time, these fields are in their ground state, their lowest energy configuration. You don't notice them. But when a field gets excited, a particle appears. The electromagnetic field, when excited, produces photons. The electron field, when excited, produces electrons or positrons. The Higgs field, when excited, produces Higgs bosons. Each field has its own properties, its own equations governing how it behaves, its own particles that arise from its excitations. These fields interact with each other. The electron field couples to the electromagnetic field, which is why electrons feel electric forces. The quark fields couple to the gluon field, which is why quarks feel the strong nuclear force. The way fields couple determines all the forces and interactions in nature. The universe is not made of particles moving through empty space. It's made of fields interacting with each other, and particles are just the observable consequences of field excitations. This perspective, central to quantum field theory, has been confirmed in countless experiments and is the foundation of the standard model of particle physics. The electromagnetic field exists everywhere, even where there are no photons. The electromagnetic field is always present, filling all of space. Even in a perfect vacuum, with no photons, no light, no radiation, the electromagnetic field is there. It's in its ground state, the lowest energy configuration, but it exists. When you turn on a light, you're exciting the electromagnetic field. The excitations propagate through space as photons, carrying energy and momentum. When you turn off the light, the photons are absorbed. The field returns to its ground state, but the field itself never disappears. This is true for all quantum fields. They're not created when particles appear and destroyed when particles vanish. They're always there, underlying everything. The ground state of the electromagnetic field is not completely quiet. Even in the vacuum, there are quantum fluctuations, virtual photons briefly appearing and disappearing. These fluctuations have measurable effects, like the Lamb shift in atomic energy levels and the Casimir effect between metal plates. The electromagnetic field, even in its emptiest state, has structure and energy. It's one of the fundamental constituents of the universe, as real as matter, as pervasive as space itself. When you kick a field hard enough, a particle appears. This is a vivid way to think about particle creation. Imagine the electron field as a car motion. Give it a jolt of energy in a small region, and a wave appears. That wave, that localized excitation, is an electron. The energy you put in becomes the mass and kinetic energy of the particle. Pump more energy into the field in the right way, and you can create multiple particles or particles with higher energy. This is what happens in particle accelerators. Protons are smashed together at high speeds. The collision dumps enormous energy into the quark and gluon fields. That energy creates new particles, sprays of quarks, gluons, and other excitations. Physicists analyze the debris to learn about the fields and their interactions. It's also what happens in the early universe. In the first moments after the Big Bang, the universe was filled with incredibly energetic fields. As it cooled, the fields settled into lower energy states, and particles froze out of the energy soup. Particle creation is not mysterious. It's just field excitation. Matter is not conserved in the sense of fixed particles. Particles can be created and destroyed freely, as long as energy, momentum, and other conservation laws are respected. The fields are what's fundamental, eternal, and everywhere. Quantum field theory successfully predicted antimatter before it was discovered. In 1928, Paul Dirac formulated an equation that combined quantum mechanics with special relativity, describing the behavior of electrons at high speeds. The Dirac equation was remarkably successful, explaining the electron's spin and magnetic properties. But it had a puzzling feature. For every solution describing an electron with positive energy, there was a corresponding solution with negative energy. Dirac initially tried to dismiss these negative energy solutions, but they wouldn't go away. Eventually, he proposed a bold interpretation. The negative energy solutions represented a new type of particle, identical to the electron but with opposite electric charge. This particle, the positron, should exist. Most physicists were skeptical. It seemed like a mathematical artifact, not a real prediction. But in 1932, Carl Anderson discovered the positron in cosmic ray experiments. It had exactly the properties Dirac predicted. This was a triumph. Quantum field theory had predicted a completely unexpected form of matter based purely on theoretical reasoning. Antimatter was real. Later, antiprotons, antineutrons, and antiparticles for every known particle were discovered. Today, antimatter is routinely created in particle accelerators and used in medical imaging. Dirac's equation, by taking quantum mechanics and relativity seriously, revealed that for every particle, an antiparticle must exist. The universe is richer than we thought, and theory showed the way. No two identical fermions can occupy the same quantum state. This is the Pauli exclusion principle, one of the most important rules in quantum mechanics. Fermions are particles with half-integer spin, like electrons, protons, and neutrons. The exclusion principle says that no two fermions of the same type can be in the exact same quantum state at the same time. Specifically, no two electrons in an atom can have the same set of quantum numbers. They must differ in at least one property: their energy level, their orbital shape, their spin direction. This principle has profound consequences. It's the reason atoms have structure. If the exclusion principle didn't exist, all the electrons in an atom could drop into the lowest energy level, and atoms would collapse into tiny, featureless blobs. Chemistry wouldn't exist. The periodic table is a direct consequence of the exclusion principle. As you add electrons to heavier atoms, they can't all pile into the lowest level. They fill higher and higher levels, creating the shells and subshells that determine chemical properties. The exclusion principle is why matter is solid. When you press your hand against a table, the electrons in your hand and the electrons in the table are forbidden from occupying the same states. They repel, not just electrically, but because the exclusion principle prevents them from overlapping. This quantum pressure is what gives matter its solidity. The exclusion principle explains why matter is solid and doesn't collapse. Without the Pauli exclusion principle, the atoms in your body, the ground beneath you, every solid object, would collapse. Electrons would all fall into the lowest energy state around the nucleus. There would be no size to atoms, no resistance to compression. Matter would behave completely differently. But because electrons are fermions, they obey the exclusion principle. Each electron must occupy a distinct quantum state. As you try to compress matter, forcing atoms closer together, the electrons resist. Not because they repel electrically, though they do that too, but because the exclusion principle forbids them from being in the same state. They're pushed into higher energy states, and that requires energy. This creates a pressure, called degeneracy pressure, that resists compression. In everyday matter, this quantum pressure is part of what makes solids rigid. In extreme conditions, degeneracy pressure becomes dominant. In white dwarf stars, electron degeneracy pressure holds the star up against gravity after nuclear fusion stops. In neutron stars, neutron degeneracy pressure does the same. Without the exclusion principle, stars would collapse into black holes much more easily. The universe would be very different. The fact that you can stand on solid ground, that objects have shape and structure, traces back to the Pauli exclusion principle and the quantum nature of fermions. Without this principle, all electrons would fall into atoms' lowest energy level. Imagine an atom without the exclusion principle. The nucleus sits at the center, exerting an attractive electric force on the negatively charged electrons. Each electron would want to minimize its energy, and the lowest energy state is the one closest to the nucleus. Without the exclusion principle, every electron in the atom would occupy that lowest state. A carbon atom with 6 electrons would have all 6 in the same orbital. A uranium atom with 92 electrons would have all 92 crammed into the same tiny region. Atoms would be incredibly small and incredibly dense. There would be no orbitals, no shells, no chemistry. The reason this doesn't happen is the exclusion principle. Each electron must have a unique set of quantum numbers. Once 2 electrons occupy the lowest energy level with opposite spins, that level is full. The next electron must go into a higher level, and so on. Electrons fill the available states one by one, climbing the energy ladder, creating the elaborate structure of atomic orbitals. This structure determines how atoms bond, how they interact with light, how they combine into molecules. Chemistry, biology, life itself, all depend on the exclusion principle, preventing electrons from collapsing into the lowest state. The periodic table's structure emerges from the exclusion principle. The periodic table is not arbitrary. Its structure, the way elements are arranged in rows and columns, reflects the quantum mechanics of electron filling in atoms. Start with hydrogen, 1 electron in the lowest energy level. Add a second electron for helium. The exclusion principle allows 2 electrons in the lowest level if they have opposite spins. That level is now full. Add a third electron for lithium. It must go into the next energy level. As you add more electrons, moving through the elements, the levels fill according to the rules of quantum mechanics and the exclusion principle. Each row of the periodic table corresponds to filling a new shell. Elements in the same column have the same number of electrons in their outermost shell, giving them similar chemical properties. The noble gases, in the far right column, have completely filled shells, making them stable and unreactive. The alkali metals, in the far left column, have 1 electron beyond a filled shell, making them highly reactive. The periodic table is a visual representation of quantum mechanics, a map of how electrons arrange themselves in atoms, governed by the Pauli exclusion principle. Dmitri Mendeleev organized the elements by chemical properties long before quantum mechanics existed. But now we understand why the table has the structure it does. It's not chemistry, it's quantum physics. Neutron stars are prevented from collapsing by quantum pressure from the exclusion principle. When a massive star runs out of fuel, its core collapses under gravity. If the star is massive enough, the collapse is catastrophic. Electrons and protons are squeezed together, forming neutrons. The outer layers of the star explode in a supernova, and what's left is a neutron star, an object about 20 kilometers across but containing more mass than the Sun. The density is unimaginable, comparable to an atomic nucleus. At this density, gravity should crush the star further, but it doesn't. What holds it up? Neutron degeneracy pressure. Neutrons are fermions, so they obey the Pauli exclusion principle. As the star compresses, neutrons are forced into higher and higher energy states because they can't occupy the same state. This creates an outward pressure that resists further collapse. The neutron star reaches an equilibrium where neutron degeneracy pressure balances the inward pull of gravity. This is purely a quantum effect. Without the exclusion principle, the star would collapse into a black hole. In fact, if a neutron star is too massive, even degeneracy pressure isn't enough, and it does collapse into a black hole. But up to about 2 to 3 solar masses, the exclusion principle saves the star, creating one of the strangest objects in the universe, held up not by heat or nuclear forces, but by quantum mechanics operating on a stellar scale. Quantum behavior disappears as systems interact with their environment. Quantum superposition, entanglement, and interference are fragile. They require isolation. When a quantum system interacts with its environment, with air molecules, stray photons, thermal vibrations, anything at all, the quantum behavior begins to vanish. This process is called decoherence. The environment acts like a constant measurement, collapsing superpositions and destroying interference patterns. Each interaction leaks information about the quantum system into the environment, and once that information is out there, spread across countless particles, the coherence is lost. The system transitions from behaving quantum mechanically to behaving classically. Decoherence explains why we don't see superpositions in everyday life. A baseball thrown through the air is interacting with trillions of air molecules, each one causing a tiny bit of decoherence. Within an unimaginably short time, any quantum behavior the baseball might have had is gone. It behaves classically. Only carefully isolated systems, like single atoms in ultra-high vacuum chambers, cooled to near absolute zero, can maintain quantum coherence long enough to observe. Decoherence is not wave function collapse, at least not exactly, but it produces something that looks like collapse. The system appears to be in one definite state, because the superposition has been washed out by environmental interaction. Decoherence explains why we don't see superposition in everyday life. You might wonder why quantum mechanics seems so strange. If particles can be in superpositions, why can't you? Why don't you see the world as a blur of possibilities? The answer is decoherence. Large objects, like you, are constantly interacting with their environment. Photons from the lights around you hit your body, scattering information about your state. Air molecules collide with your skin, your clothes, everything. The atoms in your body are vibrating, radiating heat. Each of these interactions entangles you with the environment. Your quantum state becomes correlated with the states of countless particles around you. Once that happens, your coherence is lost. Any superposition you might have been in decoheres almost instantly. You appear to be in a definite state, not because you've collapsed, but because the environment has measured you so many times, in so many ways, that your quantum behavior is completely suppressed. For all practical purposes, you're classical. Decoherence happens incredibly fast for large objects. For something the size of a dust grain, decoherence occurs in less than a trillionth of a second. For a person, it's even faster. That's why you don't experience superposition. The quantum world is hidden from you by the constant, overwhelming interaction with everything around you. The transition from quantum to classical happens through environmental interaction. There's no sharp line between quantum and classical. It's a gradual transition driven by decoherence. A single atom can behave quantum mechanically for a long time if isolated. Add a few more atoms, and the decoherence time shortens. A small molecule might maintain coherence for microseconds. A large molecule, milliseconds. A nanoparticle, nanoseconds. By the time you reach everyday objects, decoherence is so fast it's effectively instantaneous. The transition depends on how strongly the system interacts with its environment. Temperature matters. Colder systems have fewer thermal photons and vibrations to cause decoherence. Isolation matters. Systems in vacuum decohere more slowly than systems in air or liquid. Complexity matters. More internal degrees of freedom mean more ways for the environment to entangle with the system. Decoherence is why building quantum computers is so hard. You need to keep qubits coherent long enough to perform calculations, but the environment is always trying to decohere them. Engineers use extreme cooling, vibration isolation, electromagnetic shielding, all to slow decoherence as much as possible. But they can't stop it completely. Every quantum system eventually decoheres, transitioning from quantum to classical, from superposition to definiteness. from the strange world of possibilities to the familiar world of certainty. Even a single photon from your surroundings can collapse a quantum state. Decoherence can be triggered by the tiniest interaction. A photon, a single quantum of light, carrying barely any energy, can collapse a superposition. Imagine an atom in a superposition of two energy levels. A photon scatters off the atom. The photon's state becomes entangled with the atom's state. Now the information about which level the atom is in is encoded in the photon, traveling away at the speed of light. The atom's superposition is effectively collapsed. The photon has measured it. This is why quantum experiments are so difficult. Stray light in the lab, thermal radiation from the walls, even the faint glow of the cosmic microwave background, all of it can decohere a quantum system. Experimentalists go to extreme lengths to block out these influences. They work in darkened rooms, they cool systems to millikelvin temperatures, they surround experiments with layers of shielding. Even then, perfect isolation is impossible. Some photons always get through. Some interactions always occur. Decoherence is relentless. This sensitivity to the environment is both a curse and a clue. It's a curse for anyone trying to build quantum technology. But it's a clue to the nature of the quantum classical boundary. Observation doesn't require a conscious observer. A single photon can do it. The environment is always observing, always measuring, constantly pulling quantum systems toward classical behavior. Larger objects decohere almost instantly, losing their quantum properties. As objects get larger, they interact more strongly with their environment, and decoherence accelerates. A single atom can maintain a superposition for seconds in the right conditions. A molecule made of 100 atoms might maintain coherence for milliseconds. A grain of dust, a fraction of a nanosecond. A baseball, a time so short it's effectively zero. The decoherence time scales roughly with the number of particles and how strongly they couple to the environment. For macroscopic objects at room temperature in air, decoherence is essentially instantaneous. By the time you could even think about measuring a superposition, it's already gone. This is why Schrödinger's cat, a macroscopic object, is never really in a superposition. The cat, the air in the box, the walls, all of it decoheres the quantum state of the radioactive atom and the entire system long before you open the box. The cat is either alive or dead the whole time, not both. Decoherence doesn't solve all the problems of quantum measurement, but it explains why quantum behavior is hidden at large scales. The world looks classical not because quantum mechanics stops applying, but because decoherence destroys the quantum signatures before we can observe them. The quantum world is always there, underneath, but it's masked by the environment's relentless measurement. Every particle has an antimatter twin with opposite charge. Antimatter sounds like science fiction, but it's as real as the device you're using right now. For every particle, there's a corresponding antiparticle with the same mass but opposite electric charge. The electron has the positron, identical in mass but positively charged. The proton has the antiproton, negatively charged. Neutrons, which have no charge, still have antineutrons, differing in other quantum numbers. Even photons are their own antiparticles. Antimatter was predicted by Paul Dirac's equation in 1928 and discovered shortly after. Today, antimatter is routinely created in particle accelerators. Positrons are used in PET scans in hospitals. Antiprotons have been created and stored for weeks in magnetic traps. Physicists have even made anti-hydrogen, an antiproton orbited by a positron, and studied its properties. Antimatter behaves exactly like normal matter in terms of gravity, motion, and quantum mechanics. The only difference is the opposite charge and the fact that when matter and antimatter meet, they annihilate. Despite the symmetry, our universe is made almost entirely of matter. Where did all the antimatter go? Why is there an asymmetry? These are some of the deepest unsolved questions in physics. When matter meets antimatter, both annihilate in pure energy. Bring an electron and a positron together, and they don't bounce off each other. They annihilate completely. Both particles vanish, and their mass is converted entirely into energy according to Einstein's equation, E equals mc squared. Two photons are created, carrying away the energy. The particles are gone. This is annihilation, and it's the reason antimatter is so rare. If an antimatter particle appears in our matter-filled universe, it doesn't last long. It quickly finds a matter particle and annihilates. The process works both ways. If you have enough energy, you can create particle-antiparticle pairs. Smash two photons together with enough energy, and you can produce an electron and a positron. Energy becomes matter and antimatter. This is routinely done in particle accelerators. High-energy collisions produce showers of particles and antiparticles. Annihilation is not destruction in the usual sense. The energy and momentum are conserved. The particles transform into photons, which are still particles, just massless ones. But the electron and positron are gone. This process is fundamental to quantum field theory. Particles are excitations of fields. Annihilation is just one field excitation disappearing and another appearing, conserving energy and momentum. It's elegant, inevitable, and it reveals the deep interchangeability of matter and energy at the quantum level. The universe contains far more matter than antimatter, a cosmic mystery. If the laws of physics treat matter and antimatter symmetrically, then the Big Bang should have created equal amounts of both. But if that were true, all the matter and antimatter would have annihilated, leaving nothing but photons. We wouldn't exist. Clearly, there's an asymmetry. The universe has matter, lots of it, and very little antimatter. For every billion particles of antimatter in the early universe, there were about 1,000,000,001 particles of matter. The antimatter annihilated with most of the matter, leaving behind that tiny excess. That excess is everything you see, stars, galaxies, planets, you. Where did this asymmetry come from? Physicists don't know. There must be some process in the early universe that favored matter over antimatter, even slightly. Some mechanism that violated the symmetry. Theories exist, involving violations of certain conservation laws in rare particle interactions. Some experimental evidence supports these ideas, but the details remain unclear. This is one of the biggest unsolved problems in cosmology. Why does matter dominate? Why are we here instead of nothing but light? The answer lies somewhere in the first moments of the universe. In physics, we don't yet fully understand. Positron emission tomography uses antimatter to image your body. PET scans are a common medical imaging technique, and they rely on antimatter. A patient is injected with a radioactive tracer, a molecule that emits positrons. The tracer concentrates in metabolically active areas, like tumors. The positrons travel a short distance and then annihilate with electrons in the body. Each annihilation produces two gamma-ray photons, traveling in opposite directions. Detectors surrounding the patient detect these photons. By analyzing which detectors fired and when, a computer reconstructs an image showing where the positrons were emitted, revealing the distribution of the tracer. PET scans are incredibly useful for detecting cancer, monitoring heart function, and studying brain activity. They're a routine part of modern medicine, and they work because of antimatter annihilation. Positrons are antimatter, the opposite of electrons. Every time you have a PET scan, antimatter is created inside your body and annihilates milliseconds later, releasing energy that doctors use to see inside you. It's a beautiful example of fundamental physics turned into practical technology. Antimatter, once a theoretical curiosity, now saves lives every day. The quantum world is not distant or abstract. It's here now, working quietly inside hospitals and labs, making the impossible routine. Antimatter falls down, not up. Gravity affects it normally. There was a time when physicists wondered whether antimatter might fall up instead of down, repelled by gravity instead of attracted. If true, it would be revolutionary, suggesting a fundamental asymmetry between matter and antimatter with respect to gravity. But experiments have tested this, and the answer is clear: antimatter falls down, just like matter. Gravity attracts antimatter normally. Antiprotons, positrons, antihydrogen atoms, all of them experience the same downward pull of Earth's gravity as their matter counterparts. Recent experiments have measured this directly, watching antihydrogen atoms fall in a vertical chamber and confirming they accelerate downward at the expected rate. General relativity predicts this. Mass and energy curve spacetime, and both matter and antimatter have mass and energy. They should both respond to gravity the same way, and they do. This means you can't use antimatter for anti-gravity propulsion, as some science fiction has imagined. Antimatter is valuable because of its energy density, not because it defies gravity. When matter and antimatter annihilate, all their mass converts to energy. This makes antimatter the most energy-dense fuel imaginable. But it's also incredibly difficult to produce and store. For now, antimatter remains a tool for physics and medicine, not interstellar travel. Even at absolute zero temperature, quantum systems retain residual energy. Absolute zero Kelvin, is the lowest possible temperature, the point where classical physics says all motion stops. But quantum mechanics says otherwise. Even at absolute zero, quantum systems have energy. This is called zero-point energy, and it's a direct consequence of the uncertainty principle. If a particle were perfectly still, it would have zero momentum, and its position would be perfectly defined. But the uncertainty principle forbids that. There must be some uncertainty in position and momentum. This uncertainty translates into motion, into energy, even at absolute zero. Atoms in a crystal at absolute zero still vibrate. The vibrations are as small as quantum mechanics allows, but they're not zero. Electrons in atoms still orbit, or rather, exist in their lowest energy orbitals, which have energy above zero. The electromagnetic field, even in a vacuum at absolute zero, still has fluctuations, virtual photons appearing and disappearing. Zero-point energy is not a lot of energy for any single system, but it adds up. The vacuum of space is filled with zero-point energy from all the quantum fields. Some physicists speculate this might be related to dark energy, the mysterious force accelerating the universe's expansion. Whether or not that connection is real, zero-point energy is a fundamental feature of the quantum world. The universe never stops moving, not even at the coldest possible temperature. Zero-point motion means atoms never stop moving completely. Cool a substance to absolute zero, and classically, it should freeze completely. All thermal motion should cease. Atoms should sit perfectly still. But quantum mechanics forbids this. The uncertainty principle requires that even at absolute zero, atoms retain some motion. This is zero-point motion. In a solid, atoms vibrate around their equilibrium positions. At absolute zero, they vibrate with the minimum energy allowed by quantum mechanics. The vibrations don't stop. In a gas, even at absolute zero, atoms would have kinetic energy. In fact, you can't have a gas at absolute zero. Before you reach that temperature, the gas liquefies or solidifies because the atoms don't have enough kinetic energy to stay apart. Zero-point motion has real consequences. It affects the spacing of atoms in crystals, making them slightly less dense than they would be if atoms sat still. It affects chemical reaction rates, providing a baseline energy even at the coldest temperatures. It's the reason helium remains liquid at absolute zero under normal pressure. Helium atoms are so light that their zero-point motion is large enough to keep them from solidifying. you need to apply pressure to make solid helium. Zero-point motion is a reminder that quantum mechanics is always there, setting a floor on how quiet and still the universe can be. Helium remains liquid at absolute zero because of zero-point energy. Most substances freeze solid as you cool them down. Lower the temperature enough, and thermal motion stops, and the atoms lock into a crystal lattice. But helium is different. Cool helium to absolute zero at normal pressure, and it stays liquid. It doesn't solidify. This is because helium atoms are very light, and the forces between them are very weak. At absolute zero, thermal motion stops, but zero-point motion remains. The zero-point energy of helium atoms is large enough, and the interatomic forces are weak enough that the atoms keep jiggling too much to lock into a solid structure. They remain liquid, flowing freely, even at the coldest possible temperature. To solidify helium, you need to apply pressure, squeezing the atoms closer together so the attractive forces can overcome the zero-point motion. At about 25 times atmospheric pressure, helium finally solidifies at absolute zero. This behavior is unique to helium and is a direct macroscopic manifestation of quantum mechanics. Liquid helium at low temperatures becomes a superfluid, flowing without friction, creeping up the walls of containers, demonstrating quantum behavior on a scale you can see with your eyes. Zero-point energy is not just theoretical. It's the reason helium behaves so strangely, and it's a beautiful example of quantum mechanics shaping the properties of matter. This ground state energy comes from the uncertainty principle. Zero-point energy is not mysterious or speculative. It's a direct mathematical consequence of the Heisenberg uncertainty principle. For a quantum system, the product of the uncertainty in position and the uncertainty in momentum cannot be less than a certain value. If you confine a particle to a small region, reducing the uncertainty in position, the uncertainty in momentum increases. Momentum is related to kinetic energy, so increasing momentum uncertainty means the particle must have some kinetic energy. Even in the lowest energy state, the ground state, the particle cannot have zero energy. It must have at least a minimum amount, the zero-point energy. This applies to every quantum system. A particle in a box has zero-point energy. A harmonic oscillator, like a vibrating atom in a crystal, has zero-point energy. Electromagnetic fields have zero-point energy. The vacuum itself has zero-point energy contributions from all the fields that permeate space. You can think of zero-point energy as the price the universe pays for the uncertainty principle. Localization costs energy. Confinement costs energy. Nothing can be perfectly still or perfectly defined. There's always a baseline of quantum jitter, a residual motion, a ground state energy that can never be removed. Some speculate zero-point energy could be tapped as a power source. The idea is tantalizing. The vacuum is filled with zero-point energy. If we could extract that energy, we'd have an unlimited power source. This idea has inspired countless speculative theories and even some experimental attempts. But the reality is more complicated. Zero-point energy is the lowest energy state. By definition, you can't extract energy from the ground state. You can't go lower. There's nowhere for the energy to come from. It's like trying to cool something below absolute zero. It's not just hard. It's impossible. Some have argued that the Casimir effect shows zero-point energy can do work. So maybe it could be tapped. But the Casimir effect doesn't extract energy from the vacuum. It's a pressure difference caused by the vacuum. But running a machine on it would require external energy to reset the system. It's not free energy. Most physicists are skeptical that zero-point energy can be used as a power source. It's not that the energy isn't real. It is. But extracting it in a useful way seems to violate the laws of thermodynamics. Still, the question remains open at the edges of research. Quantum mechanics has surprised us before. Maybe there's something we don't understand yet. But for now, zero-point energy remains a fascinating feature of the quantum world, not a solution to our energy needs. Bose-Einstein condensates are atoms cooled until they merge into one quantum state. In 1995, physicists achieved something remarkable. They cooled a gas of rubidium atoms to a few billionths of a degree above absolute zero. At that temperature, something strange happened. The atoms stopped behaving like individual particles and merged into a single quantum state. They became a Bose-Einstein condensate, predicted decades earlier by Albert Einstein and Satyendra Bose. In a condensate, thousands or millions of atoms occupy the same quantum state. They lose their individual identities. The entire condensate is described by a single wave function. It's a macroscopic quantum object, a blob of atoms all doing the same thing quantum mechanically. Bose-Einstein condensates only form with bosons, particles with integer spin like certain isotopes of rubidium, sodium, or helium. Bosons, unlike fermions, don't obey the exclusion principle. They can pile into the same state. At high temperatures, atoms behave classically, each one independent. But cool them enough, and their quantum wave functions spread out and overlap. When they overlap completely, they condense. Condensates have bizarre properties. They flow without friction. Light slows to a crawl passing through them. They can be made to exhibit quantum interference on macroscopic scales. Condensates are a window into the quantum world, making the invisible visible. In a condensate, thousands of atoms act as a single quantum object. Imagine a cloud of atoms, each one a distinct particle, each one with its own position and momentum. Now cool them down drastically. As the temperature drops, their de Broglie wavelengths grow, the quantum waves associated with each atom spreading out. Eventually, the wavelengths become larger than the spacing between atoms. The waves overlap. At that point, the atoms lose their individuality. They condense into a single quantum state, all described by one wave function. The entire cloud behaves as a single entity. This is not a metaphor. The condensate is genuinely a single quantum object. If you disturb one part of it, the entire condensate responds coherently. If you split it in two and recombine it, you see quantum interference, as if it were a single particle passing through a double slit. Thousands of atoms interfering with themselves. This is quantum mechanics on a scale you can almost see. Bose-Einstein condensates have been used to study quantum phenomena in detail, to test quantum theory in new regimes, and to explore the boundary between quantum and classical. They're also the foundation for atom lasers, ultra-precise sensors, and quantum simulators. The quantum world is not limited to the microscopic. Under the right conditions, it can emerge at scales we can directly observe. Superfluids can flow without friction, climbing up walls. Liquid helium, when cooled below about 2 Kelvin, undergoes a phase transition and becomes a superfluid. In this state, it flows without any viscosity, without any friction. Pour it into a beaker, and it will creep up the walls, over the rim, and down the outside, dripping onto the table. It flows through tiny cracks and pores that would stop any normal liquid. It's as if friction simply doesn't exist. Superfluidity is a quantum phenomenon. At low temperatures, helium atoms form a Bose-Einstein condensate, occupying the same quantum state. The condensate moves as a coherent whole. There's no mechanism for individual atoms to scatter and lose energy. The flow is frictionless because the quantum state doesn't allow energy dissipation. Superfluids also have bizarre thermal properties. They conduct heat incredibly efficiently, far better than any normal substance. Stir a superfluid, and instead of swirling smoothly, it forms an array of quantized vortices, tiny whirlpools where the flow circulates in discrete units. These vortices are topological defects in the quantum wave function. Superfluidity is not just a curiosity. It's a macroscopic manifestation of quantum mechanics, a state of matter where quantum effects dominate even at scales you can see and touch. Superconductors carry electricity with zero resistance. Cool certain materials below a critical temperature, and they become superconductors. Electric current flows through them without any resistance. None. You can start a current flowing in a superconducting loop, remove the voltage source, and the current will keep flowing, potentially forever, without losing energy. Superconductivity is a quantum phenomenon. At low temperatures, electrons in the material form Cooper pairs, bound together by interactions with the vibrating lattice of atoms. These pairs behave as bosons and condense into a single quantum state, similar to a Bose-Einstein condensate. The condensate of Cooper pairs flows without resistance because there's no way for individual pairs to scatter and dissipate energy. Any scattering would require breaking a pair, and that costs energy the system doesn't have at low temperatures. Superconductors also expel magnetic fields, a property called the Meissner effect. Place a magnet above a superconductor, and it levitates, held up by the superconductor's response. Superconductors are used in MRI machines, particle accelerators, and experimental quantum computers. High-temperature superconductors, which work at less extreme cold, are an active area of research. Superconductivity is quantum mechanics made practical, electrons moving in perfect harmony, a glimpse of the quantum world operating at scales large enough to power technology. These exotic states reveal quantum behavior at human scales. Most quantum effects are hidden at the atomic scale, invisible to the naked eye. But superfluids, superconductors, and Bose-Einstein condensates bring quantum behavior into the macroscopic world. You can see a superfluid climbing the walls of a container. You can watch a magnet levitate above a superconductor. You can image a Bose-Einstein condensate with a camera. These exotic states of matter demonstrate that quantum mechanics isn't just a theory about invisible particles. It's a description of reality that extends to scales we can directly observe. They blur the line between quantum and classical. They show that under the right conditions, with enough cold, enough isolation, quantum coherence can survive and dominate even for billions of atoms acting together. These states are also laboratories for studying quantum mechanics itself. They let physicists test predictions, explore new phenomena, and push the boundaries of what's possible. They're beautiful in their strangeness. These states where friction vanishes, where resistance disappears, where atoms march in quantum lockstep. They remind us that the universe is richer and stranger than everyday experience suggests, and that the quantum world is always there, just beneath the surface, waiting for the right conditions to emerge. Particles don't take a single path, they simultaneously take every possible route. In the 1940s, Richard Feynman developed a new way of thinking about quantum mechanics called the path integral formulation. Instead of a particle traveling from point A to point B along a single trajectory, Feynman proposed that it simultaneously explores every possible path connecting the 2 points. Straight paths, curved paths, wildly looping paths, paths that go backward in time and forward again. All of them. Each path contributes to the final probability amplitude with a certain phase. Some paths add constructively, increasing the probability. Others interfere destructively, cancelling out. When you sum over all possible paths, most cancel. And what remains are the paths near the classical trajectory, the path that classical physics would predict. But the other paths don't disappear. They contribute, and in quantum mechanics, their contribution matters. This formulation is not just a mathematical trick. It's a deep statement about how quantum particles behave. There is no single path. The particle doesn't choose a route. It takes all routes, and the interference between them determines where it ends up. This perspective makes certain calculations easier and reveals symmetries hidden in other formulations. It's also philosophically provocative, suggesting that reality at the quantum level is fundamentally about exploring all possibilities simultaneously. Feynman reimagined quantum mechanics as particles exploring all paths at once. Richard Feynman's path integral approach offers a radically different picture of quantum mechanics. Instead of focusing on wave functions and operators, it focuses on histories. A particle getting from here to there has infinitely many possible histories, infinitely many paths it might take. In classical physics, the particle would take the path of least action, the path that minimizes a certain quantity combining kinetic and potential energy. In quantum mechanics, Feynman said, the particle takes every path, but each path contributes with a phase determined by its action. Paths close to the classical path of least action have similar phases and add together constructively. Paths far from the classical path have wildly varying phases and tend to cancel out. The result is that the classical path dominates for large, heavy objects, but for small, light particles, the contribution from non-classical paths becomes significant. This explains quantum behavior, interference, tunneling, all from this picture of summing over paths. Feynman's formulation is mathematically equivalent to Schrödinger's wave mechanics and Heisenberg's matrix mechanics, but it offers different insights. It makes the connection to classical mechanics clearer. It generalizes more easily to quantum field theory and curved spacetime. And it captures, in a vivid way, the idea that quantum systems explore all possibilities before settling on an outcome. Each path contributes to the final probability with a different phase. In Feynman's path integral, every possible path a particle might take from point A to point B contributes to the probability amplitude. Each path has an associated action, a number that depends on the path's details, and from the action, you calculate a phase. The phase is a complex number with magnitude 1, pointing in some direction in the complex plane. To find the total amplitude for the particle to get from A to B, you add up the contributions from all paths, each weighted by its phase. If two paths have similar actions, their phases are similar, and they add constructively, reinforcing each other. If two paths have very different actions, their phases point in different directions, and they partially or completely cancel. For macroscopic objects, most paths have actions much larger than Planck's constant, and their phases vary wildly. These paths cancel out almost completely, leaving only the classical path. For quantum particles, the action is comparable to Planck's constant, and many paths contribute significantly. This creates interference, quantum behavior, the rich structure of quantum mechanics. The phase is everything. It encodes the quantum nature of the path. Measuring the phase is impossible directly, but its effects, interference and probability, are observable and have been tested countless times. Paths that reinforce create high probability, paths that cancel create low probability. The magic of the path integral is in the interference. Imagine two paths from point A to point B. If their actions are nearly the same, their phases are nearly the same, and they add together, doubling the amplitude. That region of space becomes more probable. If their actions differ by just the right amount, their phases are opposite, and they cancel completely. That region becomes forbidden, zero probability. Now imagine not two paths, but infinitely many. Some regions of space receive contributions from many paths with similar phases. Those regions light up with high probability. Other regions receive contributions from paths with wildly different phases that cancel. Those regions go dark. This is how interference patterns arise. The double-slit experiment. The diffraction of electrons, all of it emerges naturally from the path integral. The particle isn't choosing a path. It's sampling all paths. and the interference between them sculpts the probability landscape. This is why quantum mechanics is so different from classical mechanics. Classical mechanics says one path is the right path. Quantum mechanics says all paths contribute, and the interplay between them determines what you observe. It's a democracy of possibilities, and the outcome is determined by how well the possibilities cooperate or conflict. This formulation treats position and momentum democratically. In Schrödinger's formulation of quantum mechanics, position and momentum are treated asymmetrically. You can write the wave function as a function of position, and momentum is represented by a derivative operator. Or you can do the opposite, but you have to choose. Feynman's path integral treats them more democratically. A path is a trajectory in spacetime, specifying both position and momentum at each moment. The path integral sums over all such trajectories. Position and momentum are both part of the story, woven together. This symmetry makes certain features of quantum mechanics clearer. The uncertainty principle, the relationship between position and momentum, emerges naturally from the path integral. So does the connection to classical mechanics, where position and momentum are both dynamical variables evolving together. The path integral also generalizes easily to quantum field theory, where you sum over all possible field configurations, not just particle paths. It's a powerful, elegant framework. And though it's mathematically more challenging than Schrödinger's approach, it offers insights that are harder to see in other formulations. Feynman's genius was recognizing that quantum mechanics could be built from a simple, intuitive idea. A particle explores all possibilities, and interference selects the outcome. Photosynthesis uses quantum coherence to transfer energy with perfect efficiency. Plants capture sunlight and convert it into chemical energy with remarkable efficiency. For decades, scientists wondered how photosynthesis could be so effective, especially in the chaotic, warm, wet environment of a living cell. Recent research suggests the answer is quantum mechanics. When a photon strikes a chlorophyll molecule, it excites an electron. That energy needs to be transferred to a reaction center where it can be used. The molecule doesn't send the energy along a single path. Instead, the excited state enters a quantum superposition, exploring multiple pathways simultaneously. This allows the energy to find the most efficient route, avoiding dead ends and energy losses. The quantum coherence, the superposition of multiple paths, persists for surprisingly long times, even at room temperature, long enough to guide the energy to where it needs to go. This quantum search algorithm, operating in the noisy environment of a living cell, achieves near-perfect efficiency. It's as if the molecule is feeling out all routes at once and choosing the best one. This discovery has profound implications. Life, at least in photosynthesis, uses quantum mechanics not as a rare exception but as a tool. Evolution has harnessed quantum coherence, optimizing energy transfer in a way that classical systems cannot match. Birds may navigate using quantum entanglement in their eyes. Many birds migrate thousands of kilometers, navigating with astonishing precision. One of the ways they orient themselves is using Earth's magnetic field. But how do they sense such a weak field? One leading theory involves quantum mechanics. Certain proteins in bird eyes, called cryptochromes, contain pairs of electrons that become entangled when struck by blue light. Earth's magnetic field affects these entangled electrons, altering the chemical reactions they undergo. The reactions produce different molecules depending on the field's orientation, and this molecular difference is detected by the bird's visual system, giving it a magnetic sense. This is speculative but supported by experiments. Scientists have shown that disrupting the entanglement disrupts the bird's ability to navigate. Magnetic fields applied in labs alter the bird's orientation in predictable ways. If this theory is correct, Birds literally see the magnetic field, overlaid on their vision, thanks to quantum entanglement occurring in real time in their eyes. It's a beautiful example of quantum biology, of life exploiting the strange rules of the quantum world to solve practical problems. The universe provides tools, quantum tools, and life has learned to use them. Birds flying across continents may owe their journey to entangled electrons, a quantum compass guiding them home. Enzymes use quantum tunneling to speed up chemical reactions. Enzymes are biological catalysts, proteins that accelerate chemical reactions in your cells. Some of these reactions involve transferring a proton or an electron from one molecule to another. Classically, the particle would need enough energy to overcome a barrier. But in many enzymes, the temperature isn't high enough to provide that energy consistently. So how do the reactions proceed so quickly? Quantum tunneling. The proton or electron doesn't go over the barrier. It tunnels through, appearing on the other side without ever having the energy to climb over. This dramatically increases reaction rates, allowing enzymes to function efficiently at body temperature. Experiments have shown that many enzymes rely on tunneling. Isotope effects, where replacing hydrogen with heavier deuterium slows the reaction, provide evidence. The heavier particle has a shorter de Broglie wavelength, making tunneling less probable. The slowdown matches the predictions of quantum mechanics. Enzymes have evolved to exploit tunneling, positioning atoms precisely to maximize the probability of tunneling events. It's quantum mechanics at the heart of biochemistry. Every breath you take, every thought you think, involves countless quantum tunneling events in the enzymes throughout your body. Life is quantum, down to its most fundamental processes. Your sense of smell might rely on quantum effects to distinguish molecules. How do you smell? The traditional theory says that molecules fit into receptor proteins like keys into locks. The shape of the molecule determines which receptor it activates, and that determines the smell. But there's a problem. Some molecules with very similar shapes smell completely different. Some molecules with different shapes smell the same. An alternative theory, proposed by Luca Turin, suggests that smell involves quantum mechanics. According to this theory, receptors detect not just the shape of a molecule, but the vibrations of its chemical bonds. Electrons in the receptor tunnel across the molecule, and the tunneling probability depends on the vibrational frequencies of the molecule's bonds. Different molecules have different vibrational spectra, like different musical chords, and the receptor detects this quantum signature. Experiments have provided some support for this idea. Molecules with the same shape but different vibrational frequencies, created by isotope substitution, can smell different to some people. But the theory remains controversial. The evidence is not conclusive, and many scientists favor the traditional shape-based model. If the quantum theory is correct, though, it means your nose is a quantum sensor, using electron tunneling to analyze the vibrations of molecules and translate them into the experience of smell. It's a tantalizing possibility, another way life might exploit quantum mechanics. Life may have evolved to exploit quantum mechanics for survival advantages. For a long time, physicists thought quantum effects were too delicate to play a role in biology. Living systems are warm, wet, and noisy, exactly the conditions that cause decoherence and destroy quantum behavior. But recent discoveries suggest otherwise. Photosynthesis uses quantum coherence. Birds may use entanglement for navigation. Enzymes rely on tunneling. DNA mutations might involve quantum effects. Even consciousness, some speculate, could have quantum underpinnings, though this is highly controversial. Life operates in a regime where quantum and classical meet. It's evolved over billions of years, exploring every possible mechanism to survive and reproduce. If quantum mechanics offers an advantage, evolution will find it. And it seems evolution has. Quantum effects can enhance efficiency, sensitivity, and speed. They allow organisms to perform tasks that would be impossible classically. This is quantum biology, a young and growing field exploring how life uses quantum mechanics. It suggests that the quantum world is not separate from the living world. We are not classical beings obeying classical laws. We are quantum beings made of quantum particles, using quantum processes, inhabiting a quantum universe. Life and quantum mechanics are not opposites. They're intertwined, and understanding their relationship may be one of the great scientific frontiers of this century. The Copenhagen interpretation says reality doesn't exist until observed. The Copenhagen interpretation, developed by Niels Bohr and others in the 1920s, is the oldest and once most widely taught interpretation of quantum mechanics. It says that the wave function is not a description of objective reality. It's a tool for predicting the outcomes of measurements. Before you measure, a particle doesn't have a definite position or momentum. It's not that we don't know those values. They don't exist. The particle is in a superposition, and the wave function encodes the probabilities of different outcomes. When you measure, the wave function collapses, and one outcome is realized. The act of observation brings reality into existence. There's no deeper level beneath the wave function, no hidden variables determining outcomes. The Copenhagen interpretation also introduces a divide between the quantum system and the classical measuring apparatus. The system is quantum, described by a wave function. The apparatus is classical, definite, and objective. Measurement is the interaction between them, where the quantum becomes classical. This interpretation has been criticized for being vague about what counts as measurement and for introducing an arbitrary split between quantum and classical. But it's pragmatic. It tells you how to calculate, how to predict, and it works. For many physicists, that's enough. The Copenhagen interpretation doesn't claim to tell you what's really happening. It just tells you what you'll observe. The many worlds interpretation suggests every quantum event splits the universe. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It says the wave function never collapses. It always evolves smoothly according to the Schrödinger equation. When you measure a particle in a superposition, the superposition doesn't collapse. Instead, the universe splits. One branch of the universe contains you observing one outcome. Another branch contains you observing a different outcome. Both versions of you exist in separate, non-communicating branches of reality. Every quantum event, every measurement, every moment of indeterminacy causes the universe to branch into multiple parallel worlds. The number of branches grows exponentially, becoming unimaginably vast. In some branches, you made different choices. In others, history unfolded differently. Quantum mechanics, in this view, is the study of the multiverse. The probabilities in quantum mechanics reflect how the branches are distributed, how much of your future selves end up in each outcome. Many worlds is controversial. It's extravagant, postulating an infinity of unobservable universes to avoid wave function collapse. But it's also elegant, requiring no special collapse mechanism, no divide between quantum and classical. Everything is quantum, always, and what looks like collapse is just branching. Some physicists find it compelling. Others think it's unnecessary metaphysics. The debate continues. In many worlds, every possible outcome actually happens in parallel universes. Imagine flipping a quantum coin, a particle in a superposition of two states. You measure it. Copenhagen says the wave function collapses and one outcome is realized, chosen randomly. Many worlds says the wave function doesn't collapse. The universe splits into two branches. In one branch, you observe heads. In the other, you observe tails. Both outcomes happen. Both versions of you exist, each convinced they experienced a definite result, unaware of the other branch. This splitting happens constantly at every quantum event. Every radioactive decay, every photon interaction, every moment of quantum uncertainty, the universe branches. The number of branches is incomprehensibly large and growing exponentially. Somewhere in the multiverse, there's a version of you who made every possible choice, experienced every possible history allowed by quantum mechanics. This is either profound or absurd, depending on your perspective. Critics argue it's untestable, that postulating an infinite number of unobservable universes is unscientific. Proponents argue it's the simplest interpretation, requiring no additional mechanisms beyond the Schrödinger equation. The mathematics of many worlds is identical to other interpretations. The difference is philosophical. Is reality one world with probabilistic outcomes, or is it a vast multiverse where all outcomes occur? The answer, if there is one, lies beyond what experiments can currently tell us. The pilot wave theory proposes hidden variables guiding quantum behavior. Pilot wave theory, also called de Broglie-Bohm theory, offers a deterministic alternative to standard quantum mechanics. It says particles have definite positions and trajectories at all times. There's no superposition of position. A particle is always somewhere specific. But guiding the particle is a wave, the pilot wave, which evolves according to the Schrödinger equation. The wave guides the particle's motion, determining its velocity at each moment. The particle follows a definite path, but the path depends on the wave, which can extend across space, creating non-local effects. In the double-slit experiment, pilot wave theory says each particle goes through one slit, but the pilot wave goes through both. The wave interferes with itself, and the interference pattern guides the particle's motion, creating the observed distribution on the screen. This theory reproduces all the predictions of standard quantum mechanics, but does so with hidden variables, the particle's position and the pilot wave. It's deterministic. If you knew the initial conditions precisely, you could predict the future. But in practice, the initial conditions are unknowable, so the theory looks probabilistic. Pilot wave theory has been around since the 1920s, but remains a minority view. It requires non-locality, instantaneous influences across space, which some find troubling. But it offers a clear, visualizable picture of quantum mechanics where particles have definite properties, even when not observed. After nearly a century, physicists still disagree on what quantum mechanics means. Quantum mechanics is the most successful scientific theory in history. Its predictions have been tested to extraordinary precision and never found wanting. Technological revolutions have been built on its principles. Yet after nearly 100 years, physicists do not agree on what the theory means. What is the wave function? Is it real or just a tool? Does it collapse or does the universe split? Are there hidden variables or is randomness fundamental? These are not minor details. They're questions about the nature of reality, and quantum mechanics doesn't answer them. Different interpretations, Copenhagen, many worlds, pilot wave, and others, give different answers, and experiments haven't definitively ruled out any of them. Some physicists think this is a problem, a sign that our understanding is incomplete. Others think it's just philosophy, irrelevant to doing science. The mathematics works, the predictions match experiments, and that's what matters. But the questions linger. What is really happening in the quantum world? When we're not looking, does the universe have definite properties, or does it exist in a haze of potential? The measurement problem, the role of observation, the nature of probability, all remain open questions. Quantum mechanics has transformed our world, but the world it describes remains, in some deep sense, mysterious. Quantum cryptography creates perfectly secure communication using entanglement. Quantum mechanics enables a new form of cryptography that's provably secure. The idea is to encode information in quantum states, like the polarization of photons, and send them between parties. If an eavesdropper tries to intercept and measure the photons, they disturb the quantum states. The laws of quantum mechanics guarantee that this disturbance is detectable. The communicating parties can check for signs of eavesdropping and, if detected, discard the compromised data. If no eavesdropping is detected, the remaining data is secure. No algorithm, no computational power can break quantum cryptography because it's not based on mathematical difficulty. It's based on the fundamental laws of physics. Measuring a quantum state disturbs it. You can't copy a quantum state perfectly. These facts make quantum communication secure. Quantum key distribution, a practical form of quantum cryptography, has been demonstrated over hundreds of kilometers using fiber optics and even via satellite. Governments and corporations are beginning to deploy quantum, secure networks. This is quantum mechanics turned into security. The strange, counterintuitive properties of quantum systems, once just curiosities, are now protecting information from the most sophisticated attackers. It's a beautiful example of how understanding the quantum world leads to technologies that would be impossible in a classical universe. Quantum sensors detect gravitational waves and map underground structures. Quantum mechanics allows for sensors of extraordinary precision. Quantum sensors exploit superposition, entanglement, and interference to measure tiny changes in physical quantities. One example is atomic interferometers, which use atoms in superposition to measure acceleration and rotation with incredible accuracy. These sensors can detect gravitational waves, ripples in spacetime from distant cosmic events. They can map variations in Earth's gravitational field, revealing underground structures like oil deposits or aquifers. Another example is QUIDs, superconducting quantum interference devices, which measure tiny magnetic fields. They're used in brain imaging, detecting the faint magnetic signals from neurons. Quantum sensors can measure time, electric fields, temperature, all with precision far beyond classical sensors. The reason is quantum coherence. A quantum sensor in a superposition samples multiple values simultaneously and uses interference to amplify small signals. The catch is that coherence is fragile. Environmental noise causes decoherence, limiting sensitivity. But with careful engineering, quantum sensors can operate long enough to detect signals that would be invisible to classical devices. This is quantum technology, already deployed and making measurements that seemed impossible a few decades ago. The quantum world is not just theory. It's a toolkit for exploring reality with unprecedented precision. Quantum computers will solve problems impossible for classical computers. Quantum computers are not just faster versions of classical computers. They're fundamentally different machines that solve certain problems in entirely new ways. A classical computer processes information using bits, each 0 or 1. A quantum computer uses qubits, which can be in superpositions of 0 and 1. With many qubits entangled together, a quantum computer can explore an exponentially large space of possibilities simultaneously. For certain tasks, this provides an enormous advantage. Factoring large numbers, which is hard for classical computers and underpins modern encryption, can be done efficiently on a quantum computer using Shor's algorithm. Simulating quantum systems, which is exponentially hard classically, is natural for a quantum computer. Searching databases, optimizing complex systems, and solving certain mathematical problems all benefit from quantum algorithms. But quantum computers are not magic. They won't speed up all tasks. Many everyday computations are still better suited to classical computers. The challenge is building large, stable quantum computers. Qubits must remain coherent long enough to complete calculations, but decoherence is always threatening. Error correction is essential but requires many physical qubits to encode a single logical qubit. Despite the challenges, progress is rapid. Quantum computers with dozens of qubits now exist, and rudimentary quantum algorithms have been run. In the coming decades, quantum computers may revolutionize fields from drug discovery to cryptography to artificial intelligence. Quantum supremacy was achieved when quantum computers outperformed conventional ones. In 2019, Google announced they had achieved quantum supremacy, also called quantum advantage. They built a quantum computer with 53 qubits and used it to perform a specific calculation. The task was designed to be hard for classical computers, sampling the output of a random quantum circuit. Google's quantum computer completed the task in 200 seconds. They estimated the best classical supercomputer would take 1,000 years. This was a milestone. For the first time, a quantum computer had done something a classical computer couldn't do in a reasonable time. Critics pointed out that the task was somewhat artificial, chosen to favor the quantum computer. It didn't solve a useful problem, and improvements in classical algorithms later reduced the estimated classical time to days or weeks, not millennia. But the achievement stood. Quantum supremacy had been reached. Since then, other groups have demonstrated quantum advantage in different tasks. The gap between quantum and classical is growing. We're entering an era where quantum computers can do things classical computers cannot, at least for certain problems. This is the beginning. As quantum computers grow larger and more stable, their advantage will expand. Tasks that are currently impossible will become routine. The quantum revolution in computing is not speculative. It's happening now. The quantum internet will connect quantum computers across the globe, just as the internet connects classical computers, allowing them to share information and collaborate. A quantum internet would connect quantum computers using quantum communication. Information would be transmitted not as classical bits but as qubits, quantum states that can be in superposition and entangled. This has profound implications. Quantum computers at different locations could be entangled, allowing them to work on problems together in ways impossible classically. Quantum cryptography would enable perfectly secure communication across the network. Quantum sensors separated by large distances could be linked to improve precision. Distributed quantum computing could tackle problems too large for any single machine. Building a quantum internet is technically challenging. Qubits are fragile and decohere quickly, so transmitting them over long distances is difficult. Researchers are developing quantum repeaters, devices that extend the range of quantum communication by refreshing entanglement without measuring the qubits. Satellites are being used to distribute entangled photons across continents. Fiber optic networks are being equipped with quantum capabilities. The quantum internet is not a distant dream. Prototype networks exist in labs and are being tested in the field. In the coming decades, a global quantum internet may emerge, fundamentally changing how information is shared and processed. It will be the infrastructure of the quantum age, connecting the quantum technologies of the future. You've traveled deep tonight, down into the quantum world, the foundation of everything that is. The particles that make you, the light that touches your eyes, the forces holding atoms together. All of it follows rules that seem impossible, yet they're the deepest truths we know. Superposition, entanglement, uncertainty, tunneling. These aren't just abstract ideas. They're the way the universe works, the silent machinery running beneath every moment of existence. It's strange to think that the solid world around you, the one that feels so definite and real, emerges from a quantum foundation where nothing is certain until it's observed, where particles exist in many states at once, where distance loses its meaning. And yet here we are, made of quantum parts, following quantum rules, somehow experiencing a classical world. Perhaps the quantum realm feels distant, too small, too strange to touch your life. But it's not distant at all. It's here, in the atoms of your body, in the light of the stars, in the energy powering your thoughts. The universe is quantum, through and through. And that makes it more mysterious, more beautiful, more full of wonder than we ever imagined. Rest now, and let these ideas drift through your mind, like waves interfering, like particles tunneling through the dark. Sleep well.